So I guess it's about time, right? It's 5 o'clock. So maybe we should start, right? Okay. So good afternoon, everyone, and welcome to the third lecture of this summer school, now about sequence models. It is my great pleasure to introduce you Noah Smith, one of the speakers that has been with us since the very first edition back in 2011, so 10 years now. Noah is professor at University of Washington and senior researcher manager at the Allen Institute for Artificial Intelligence. His research has been very active in the fields of natural language processing, machine learning, and computational social science. So Noah is a very enthusiastic speaker, so I hope you all enjoy the lecture. We can probably, I don't know if you want to say a few words, Noah?
Nice to be here. Excited to engage with you guys. I hope you enjoy the lecture. Hey, Andre. I'll be here and watching the channel and look forward to talking with you.
Hi, everyone. Today I'm going to be talking to you about sequence models, one of the most important core elements of the foundations of natural language processing and machine learning. And a large part of this lecture is really material that doesn't change very much year to year. There are definitely new developments in how we do sequence modeling today. It's quite different than it was 10 or 20 years ago. But the foundations kind of stay the same. And I think understanding today's large data, large scale, deep architecture sequence models hinges on having a foundational understanding of the earlier things, which fortunately for us are pretty straightforward and pretty cool. So let's dive in. Today's lecture is going to have 5 parts. We'll start out by talking about the simplest kinds of sequence models, known as Markov models. And then we'll add the word hidden to the front of that label and talk about a famous family called hidden Markov models as applied in natural language processing for discrete data. And a big part of understanding hidden Markov models is understanding the key algorithm that we use when we use a hidden Markov model. It's called the Viterbi algorithm, and we'll spend some time on that. But it's not the only one. So we'll also discuss several other inference algorithms that are used with hidden Markov models. And finally, we'll talk about learning. This lecture is going to be segmented into, I think, 6 parts, each about a half an hour long, give or take. Okay, so diving in, Markov models. One way to think about a piece of text, like a document or a paragraph or a sentence, is that it's simply a sequence of symbols. And depending on a number of factors, you might think about these symbols as being the bytes or the letters, or maybe we're not looking at an alphabetic language and we're talking about characters. If we have a more linguistically pre-processed piece of text, we might have broken words down into morphemes, and we might think about each symbol as being a morpheme. Most commonly, we start from the idea that the text is a sequence of words. And we're not going to talk today about how we break the text into the words. We're going to assume that that's been handled for us. So I'm going to use the symbol sigma to denote the set of symbols. So these will be usually our words in the vocabulary. And so once we sort of lay that out, we realize there are a lot of possible sequences that we could build. In fact, there are infinitely many. We use, by the way, sigma star to denote the set of all possible sequences of any length. So we're borrowing here from formal language and automata theory, if you're familiar with that area, if your background is in computer science. So there are infinitely many sequences. And the first task we're going to lay out for ourselves today when we talk about Markov models and language modeling is that we want to define a probability distribution over the event space of sigma star. Meaning, we're going to assign some probability to every possible sequence that we could build out of the set of symbols sigma. Okay, pop quiz. You have some background and a lecture already in machine learning, at least. we talk sometimes about two families of approaches in machine learning, generative and discriminative. From the very little that I've said so far, I want you to think about this. Which kind of machine learning hat am I wearing? Am I talking about generative machine learning or discriminative? I'll wait a second while you think about it. Okay, so to dive in a little more on this, generative models are models that tell some kind of a mythical story to explain where our data came from. They are often used these days in various use cases to sample fake data. So with a generative model, you can generate a sample from the distribution and see something that isn't real data, but maybe looks, if you've done a good job with your modeling, looks like real data. A discriminative model, on the other hand, is more like the sorting hat in Harry Potter. It takes an input and it does a task. Often it sorts examples or classifies things. So if you said what I was talking about with this probability distribution over sequences sounds like a generative model, you were right. This entire lecture is going to be on the generative side of machine learning. We're thinking about models that can be used to generate. Note, that doesn't mean that's the only way we use them. Generative models can be used to do a lot of different things, including discriminative tasks. But their starting point is the idea that we're building a probability distribution over the data space. Okay, so I like to start out when we tackle a hard problem, like how do we build a distribution over sigma star, with simple, perhaps slightly stupid solutions. So I'm going to give you a couple trivial distributions so that you understand why we build the things we build. So here's a very simple thing you can do. You can just say there's a max length, B, and any sequence that's longer than B gets 0 probability, and then define distribution over everything that's left, everything that's shorter, B or shorter, sequence symbols long, give it a uniform distribution. It works, right? It will sum to 1. We know that there's only a finite number of sequences that are length B or shorter, and so we no longer have this sort of infinity problem. So thinking about this solution, it's probably not a very good solution because we never really know what the max length of a sequence might be. Natural language is surprising, and if you look at a distribution of text, you'll often see some very long examples, surprisingly long. So this isn't very satisfactory, but it's sort of mathematically correct in the sense that we'll have a distribution and the probabilities will sum to 1. Another sort of simple solution that's worth thinking about is to say, well, we ought to use data. There's really not much point in building probability distributions if we never look at any evidence. So we could take a corpus of examples, say we have n of them, and give 1 over n probability to each sequence that we observe, and then 0 probability to all the rest. So this is also correct mathematically. The numbers will sum to 1, but it has this kind of annoying property that we're giving 0 probability to a lot of sequences, basically any sequence we've never seen before. So this model won't generalize at all, right? It's only putting probability on things that it's seen in the past. So really, when we talk about language modeling, when we talk about building probability distributions over sigma star, we want to make sure that every sequence that could ever occur will have non-zero probability. That kind of guarantee has been traditionally considered very important as sort of a starting point for making sure that our model generalizes to new data. We don't know what people will say tomorrow. We need to be ready for anything. So we want to make sure that every sequence gets some very small probability at least. So in order to do that, if you want to put probability on this infinitely large space, you have to design some kind of probabilistic model family, and then propose some algorithms that will let you construct the model from data in a way that once you've constructed it or once you've estimated the parameters, it will generalize to new instances. Okay, so here we go. Our starting point for thinking about distributions over sequences is a model we'll call the history-based model. And so we've started introducing some mathematical notation. We're going to define the probability of a sequence W1 through WN. We're going to add a little bit of notational stuff to make this work out elegantly as we go forward. When we think about this sequence, we're always going to assume there's a special start symbol at the beginning, which is different from any of the words, and a special stop symbol at the end. And these are to help us make the notation a little bit simpler, and also to help us make sure that the probabilities sum up to 1 when we get to the end. So what we're going to do is we're going to take the probability of this whole sequence from the start symbol through the words to the end, the stop symbol, and we're going to decompose it into a product of probabilities of each word on its own conditioned on the words to its left. Okay, so without loss of generality, the probability at position I will be the probability will be denoted by gamma of Wi given W1 up through Wi minus 1. And implicitly, the start symbol is also over there on the right side of the conditional bar. We're not making any assumptions here. This is not an approximation. This is always going to be true for any joint distribution because of the chain rule. In fact, you could write this a lot of different ways. You don't have to order the words one after the other, left to right in sequence. It's just convenient to do that, and it sort of has a nice, almost psychological plausibility to imagine that each word is generated, is caused by or depends on the words that came before it to its left. So each word is generated under this model from left to right, conditioned on everything that came before. So I like to kind of visualize these models by imagining that we're going to toss a die or some dice. By the way, a lot of people don't know this fun fact about English. We often talk about rolling dice, which is the plural. The singular of this weird, irregular word is die. So we're going to roll a die at each position to decide what word comes up. And I want you to imagine a die with many sides with a word printed on each side. So this die doesn't have 6 sides like a normal one. It's actually got like 10 or 20 or 30,000 sides, one for every word in the vocabulary, and it's weighted in such a way that the probabilities are maybe different for every word. Anyway, here's what it will look like. We write down the start symbol. We're about to generate a sequence. We're going to pick up the die that corresponds to the history that is just the start symbol and nothing else, and we're going to roll it. And let's say we roll the word I. And so we write it down, and now we're going to go pick up the history that corresponds to start followed by I. And we're going to roll that one. And we're going to get the word want. And we repeat. Now we have start I want as the history. The next time we have start I want A, we roll the word flight. Next we have start I want a flight, and then we roll 2, and we keep going, each time picking up the die that corresponds to the entire history up to this point. And we go until we roll the stop symbol, which, by the way, should also be printed on one side of the die. This guarantees that we're only going to put probability on finitely long sequences. If we didn't have probability of a stop at every position, then we could conceivably keep going on forever. Okay, so there we are. That's how we generate a sequence with this history-based model. This is a very rich model. In fact, it can represent any distribution over the sequences because we haven't made any independence assumptions about the words. Every word depends on all the words that came to its left. How many parameters does it have? This is a kind of a complicated question. One way to think about the number of parameters in this kind of die-based model is that you have one probability value associated with every word plus the stop symbol on each die. So size of sigma times the number of dice is going to give you the total number of parameters you need. But this is a little bit of a trick question. Remember, we have a separate die for every history that we could have ever seen going all the way back to the start symbol. And it's pretty easy to see there are infinitely many of those. So this is a model that has really an arbitrarily large number of parameters. And because we'll never have seen most of the histories with finite data, we actually don't have a really good way to estimate a lot of the parameters associated with some of these, with most of the dice. So here's the thing that kind of kills this model. We always need to ask, how do we get the probability of a sentence that was not seen in the training data? Because there are going to be a lot of those. And the answer is that this model doesn't leave any probability at all allocated for models that were not seen. There is simply no way to assign positive probability to a word with this. There is no way to assign probability to a sequence with a history that we never saw, because we don't know how to estimate the values on that die. So this is a model that just doesn't, no matter what you do for the histories you've seen, it'll never be able to tell you what to do for the histories you haven't. So it's sort of undefined. Okay, so we're going to go to a different model that makes a very, very strong independence assumption that is very convenient and makes things very simple. And this is a very easy to understand model, and it's very widely recognized. It has a number of names, but the one that we'll start with, we'll call it the bag of words model. And the idea is you're going to just assume that every word is completely independent of every other word in the sequence. Okay, so the math is on the slide. You simply have a gamma term for each W in the vocabulary, including the stop symbol, and the probability of the sequence is the product of the probabilities of each of the words. Another way to say this is that we only have one die total for the whole model, just one die with all the words and stop written on it. And we just draw each word, not conditioning on anything, one after the other, until we get to the stop symbol, and then we're done. Very, very simple model, very strong assumption. What this strong assumption means is that you can't really fit the data very well. One sort of annoying property about this model is that the order of the words has no effect at all on the probability. So if you take a sentence like, I want ice cream, the probability of that sentence is exactly the same as want I ice cream, or cream ice want I, or ice cream want I. All orderings of the same sequence will have exactly the same probability, even though some of these are good English and some of them are not. How many parameters? Well, remember our trick. The number of parameters, or the number of probabilities we have to estimate in this die-based model, is equal to the size of the vocabulary times the number of dice. And there's only one. So it's size of sigma. Well, really size of sigma plus 1 to leave some probability for the stop symbol. What about sentences not seen in training data? The news here is much better than it was for the last model. The probability of a sentence not seen in the training data is going to be positive as long as all of the words have positive probability. So that means as long as you make sure that every word in the vocabulary has some value greater than 0 associated with it, either because you saw it in the training data and therefore gave it a probability estimate that was non-zero, or because you did something extra when you estimated the probabilities to smooth out the probability mass. We'll talk a little bit more about smoothing later. Then you're fine. As long as the new sentence doesn't contain unseen words, you should be okay. Okay. So we'll come back to this point, but basically things look much better for this kind of model. Okay, so here's a model that's sort of in between the two. It's called a first order Markov model. And maybe it's a happy medium between the history-based model that sort of just memorizes the data and can't generalize well, can't deal with new histories, and the Unigram model, which makes a very strong, sort of linguistically stupid independence assumption. This model conditions each word on the single most recent symbol in the history, or the last word. So you have one die per history, but the histories each correspond to a single word. So the number of dice is now the size of the vocabulary, plus 1 for start. So when we start out, we pick up the start die and we roll it. Then we pick up the I die and we roll it to pick the next word want. Then we pick up the want die and we roll it and we get the next word A, and so on. So notice that we don't have this sort of combinatorial explosion of dice. We just have one die for every history word. And we keep going until some die rolls us a stop. So this is a nice model, first order Markov model. It makes a weaker independence assumption than the bag of words model. It says that each word depends on its history only through the most recent word. This is often called a Markov assumption. And the number of parameters sits between the sort of infinite parameter model that we had with the history-based, the full history-based model, and the single die model with only size of vocabulary parameters. This one has order of size of vocabulary squared, because you have one die for every history word, and every word appears on each of those dice. What about sentences not seen in training? Here, it's a little bit more complicated than it was with the bag of words model. We have to make sure that even if we never saw a word in the training data, we still estimate probabilities for its die so that it can be a history word in new data at test time. And we have to make sure that each die puts non-zero probability on each of its faces. If we do those two things, we should be okay. And there are standard techniques for doing that. Okay, now, you may have the sense that, that we can generalize these ideas, and in fact we can. So here's the very general formulation of mth order Markov models. So I'm using M to denote the Markov order. And the Markov order is the number of words in the most recent part of the history that you consider when you generate the next word. So the bag of words model is a 0th order Markov model because it doesn't condition words on any of the history. And at the extreme end, where we go toward infinity, we get the entire history model that looks at the entire past all the way back to the start symbol. If we fix any value in between, call it M, we have an mth order Markov model. The first order Markov model is, of course, M equals 1. And the math on the slide shows you what the formula looks like for an arbitrary order Markov model. And so you can think of these as living on a spectrum, and at the left extreme where we have fewer parameters, just size of vocabulary parameters, one die, we make very strong independence assumptions. And at the right end, as we increase M, we increase the expressive power of the model, but we also increase the number of parameters. So we can fit the training data better, but we have a lot more parameters, and we run an increasingly greater risk as we go to the right of overfitting to the training data and essentially moving towards memorization rather than being able to generalize to new examples. This is kind of fun. I took a corpus of about 2.8 million words from American political blogs. This was, I think more than one election cycle ago, so hopefully not too depressing. This amount of data is small by the standards of today's large language models, but it's much larger than it was when I started out in the field. So it gives you a sense things continue to change and increase, but this amount of data it's sufficient to see some differences between what happens when we build a language model with different orders of Markov assumptions. So this is a Unigram model. Unigram, by the way, is another name for the bag of words model. It's called a Unigram model because a gram is like a symbol, one symbol. Uni, one, meaning the probability is associated with a single symbol. So here I'm just rolling the die, and I generated some sequences, and you can see they're what we call word salad. They don't make any sense. They don't flow. They don't sound like English. They're just words. The only thing that's sort of correct about them is that the words tend to occur in the right proportion. So words like this and it and I and the appear with reasonably high frequency, as they do in normal English text, or at least normal English text on American political blogs. Here's a Bygreen model. That's another name for the first order Markov model, where we condition on one word. So now each probability is associated with two words in sequence, the one we condition on and the one we generate. And here things are starting to sound like slightly more English-like. The lack of the Senator McCain hadn't keep this story backwards. It's not grammatical. It doesn't make sense. But it's locally, it starts to get a little better. And as we move to the trigram model, now we're conditioning on two words of history, M equals 2. It starts to get almost realistic. So as I can pin them all, none of them want to bet that any of them might be. Okay, not great. Conservatism unleashed into the privacy rulebook, and when told about what Paul, not grammatical, but starting to sound increasingly like English. When we get to 5 grams, if you weren't paying attention, this would totally pass as English. Like if it was on the radio in the background and you weren't really listening, he realizes fully how shallow and insincere conservative behavior has been. He realizes that there is little way to change the situation. Like, that's not bad. I don't know what they're talking about. It might not make sense in any context. It's not grounded in anything in the real world, but it passes more or less as English. When we go to 100 grams, which is effectively memorizing the data, we essentially are just resampling sentences from the training data. I think this is an exact quote from some of the training data. Okay. I think that's a great place to pause.
So I guess now we can take questions.
Yeah, we
for a
have
few
one
minutes.
in the Q&A right now.
Right. What is m equal to when it's a unigram? I thought it would be equal to 1. Okay. So this is a little confusing. So there are sort of two related concepts. One is the Markov order, which is how many words of history do I depend on? And the other is the word that makes its way into the name of the model, like uni and unigram or bi and bigram. And you'll notice that in the lectures, I always call it an m+1 gram, because the Markov order is always one less than the name. The reason is that the word unigram or bigram or trigram is referring to the number of words in the tuple associated with a conditional probability. So it's including the predicted word along with the history. So in a trigram model, you have 2 words of history and 1 predicted word. The parameters are associated with the trigrams. The Markov order is 2 because the history length is 2. It's a little confusing and weird. And if we reinvented the notation today from scratch, we'd probably come up with something better, but we can't change history. Okay, next question. Can you once more explain the dice part for the first case before the bag of words case? Right. So this is the weird model. When I teach this class, this lecture, I sometimes call it the creepy model, because it essentially memorizes the history. Every word is conditioned on everything that ever came before it. And you accomplish that by having 1 die for every history of any length. And so you keep, you have to have a die for every history, and that's infinitely many dice. And this model really, you can show that all it will do is memorize the data that it's seen. It will not be able to do any generalization at all. Okay, I'm taking these in the order that they're appearing on my screen. I think they get upvoted, so apologies if I don't get to your question in a fair order. Is there a specific reason why the smaller number of the grams was the shorter that generated the sentences? So I think what you're getting at is that we tended to see shorter sentences with a smaller engram. I don't think a priori there's any reason to expect that. Basically, what all of these models are doing is fitting something kind of like a geometric distribution to the lengths. And the nature of that geometric distribution will become a little bit more probably higher variance as you get to longer engrams, because the length will depend essentially on the most recent history. So off the top of my head, no, I don't think a priori I would expect that a shorter engram would lead to shorter sentences, but you might be able to prove that that would happen. But it's not obvious to me. Okay, next question. So what's the best engram model, 2 gram or 3 gram? Well, right, it depends on your task and how much data you have. When I was a grad student, the conventional wisdom was that trigrams are great. It's really hard to beat the bigram, to beat the trigram. Basically, everybody was using trigrams for speech and machine translation. And over the course of the next 5 or 10 years, 5 grams emerged. And the reason 5 grams were better then was because we had more data, and therefore we could actually estimate the 5 gram model, whereas before it would overfit. And so now these are not the fashionable models anymore. So it's sort of like situation dependent. It depends on your computational limitations, and ultimately it's an empirical question. In any given setting, if you know you want to use an Engram model, you're probably going to want to try a few different variations and see what fits your data and your limits. In what practical situations bag of words could be useful? This is a great question. So it turns out that for a lot of relatively simple, what we today consider simple retrieval tasks, like I want to find a relevant document given a query in a large collection, or I want to filter on whether a concept is present or absent in a document. These things come up often in very applied settings. In my work, I see them sometimes in social science projects. Bag of words models can be very very effective for simple filtering and retrieval kinds of problems. Not so effective when you have fine-grained information needs, or you want to do a really high precision job of filtering document. Suppose we have a trigram with one word present in the vocabulary and one word not in the vocabulary. What would happen then? Well, the trigram as presented and as conventionally used, if the trigram includes any words at all that are not in the vocabulary, then it's unknown. There's no unless you change the unknown word to a special symbol called out of vocabulary, and when you trained the model, you estimated probabilities with out of vocabulary symbols, in which case out of vocabulary is really a special vocabulary symbol, then it won't, your model won't know what to do. It's a 0. Connecting to Marco Guido's question, since the probability is assigned to a 1-word portion of text or to a 100-word portion of text, is this explaining the fact that sentences are longer or shorter? Yeah, so one way to think about this is that every length of text has some probability associated with it. The probability of a sequence that is 99 words long is the sum of the probabilities of all 99-word sentences. And if you add that up, you can actually add that up by summing up the probabilities in a particular way. If we had a 20 minutes on a whiteboard, I could work through it with you, and basically show that what you're getting is a geometric distribution. So there will be some probability allocated to every length up to arbitrarily long. It will get smaller and smaller exponentially. So the numbers will be very tiny as you get to longer sequences. But it turns out this works reasonably well for natural language. Nowadays, engrams are used more for letters and words. Are we just overloading the engram? Yeah, this is a great question. All of the terminology that I'm using here, all of the mathematical tools can be like I think I said at the beginning. Actually, what the symbols are, I usually default to words because that's usually where we think about applying language models. But you can do the same thing at the character level, and Engram models at the character level can be really one really useful place for them is in language identification. You can do pretty good job of language ID, even in very noisy text, if you use engrams. But it's still an engram model, right? Engram doesn't make using that term doesn't imply a commitment to doing things at the word level. It looks like there are some questions in the chat as well. I'll pull that up. Is BERT considered a generative model? I know it's difficult to generate text with it. Is the fact that it looks at the future of the sequence what makes it unable to do this kind of sampling given the history? What's the theoretical explanation for that? This is a great, I love this question. BERT isn't really a generative model. The issue is that when you're estimating BERT, the probability that you're estimating is a conditional probability of a word given its context on both sides. And so, if you draw out the full probability graph, you'll see later in the lecture I get to talk about probabilistic graphical models a bit. And if you were to try to draw a probabilistic graphical model for BERT, it would have cycles. It would be loopy. Words would depend on each other in a way that basically makes it impossible to sample directly from the distribution. If you can't linearize the events so that every event comes strictly before some events and strictly after others, then you can't really generate from the model in any meaningful way, and you really don't have a generative model. That said, the estimator that BERT is using, when I saw the BERT paper originally, it reminded me of some weird estimators that people cooked up in the 1970s called pseudo-likelihood. And I've talked about this with a lot of people. It's not pseudo-likelihood, but it's also not that far from a reasonable thing you might do with some kinds of generative models. So I think, and I think Cho at NYU has thought about this a little bit and maybe even written some papers on it. Where I am on this right now is that BERT is kind of a hack. It's not really a generative model, but it's probably not a ton of work to come up with a variant of BERT that could be seen seen as an estimator for a generative model that you could sample from. But I haven't actually seen that done. But this is basically, yes, this is why people can't sample sentences from BERT using conventional methods. Like with the models I showed, you can go left to right, or GPT. All the GPT models are left to right. So they are proper generative models. Somebody asked to copy this into the Q&A. I will ask one of the organizers to do that if they want to do that. And then there's something in, looks like Portuguese. I don't speak Portuguese, unfortunately. Okay, one more. Would a language model for subword units be useful? Has it been done? One would have a lot less vocabulary. Yeah, this is something you can totally do. So things like word pieces and BPE encoding have become very popular in machine translation. So you could, if you have a transformation like that, you could apply it to your text and then estimate a language model. And people have done this. Another thing is sort of linguistically informed language models where you segment the words based on the morphology of the language. If you have a good morphological analysis tool, you could pre-process your text, make it into morphemes, and then maybe have a better language model because now your vocabulary is smaller and you get better sharing of statistics across the vocabulary. It's a great idea. And people have done a lot of different variations on this. Yeah. Okay. No open questions. I'm not keeping a close eye on time. Let's go. Why don't we go on with the next chunk of the lecture?
Okay, welcome back. Picking up where we left off, we were talking about M+1 gram models, also known as Markup models. And I want to quickly review pros and cons for these families of probability distributions for sequence modeling. On the pro side, these models are really easy to understand. They provide a sort of a theory or a formalism for how language works. Each word is generated, conditioned on its history in turn. The model is fully generative. As we'll see in a minute, it's very easy to generate new sequences like I did at the end of the last slice of the lecture. We'll talk through several algorithms for useful things you'd like to do with these models, and we'll find that each one is incredibly simple and intuitive. On the downside, this formalism that we associate with these models, or the theory that they sort of assume, is obviously wrong. We don't generate language one word at a time without considering a longer history or the context in which we're talking. And so this is not a great theory. Linguists tend not to love M+1 gram models or find them particularly interesting or useful. In fact, Chomsky famously said that they didn't make any sense way back in the 1960s, I think. Further, as your Markov order M gets larger, you're going to find more and more histories that you're going to observe a smaller and smaller fraction of the possible histories and words with those histories. So data sparseness is going to increasingly become a problem. You're going to have a lot of zero counts. And we'll talk a little bit more about how we estimate the parameters of the model. But one of the key things that becomes an issue is that you have to find cleverer and cleverer ways to smooth out the probability mass to make sure that every M+1 gram gets a non-zero value. And then finally, we said at the beginning, we assume a fixed vocabulary that's known at the beginning of training and never changes. That is not very practical, because with realistic data, we're going to see new words all the time, and our probability model will not know what to do with them at all. We're not going to talk too much about ways to deal with this issue. It's still an ongoing problem with language modeling, even in current research today. Okay, so I want to drill into 4 different algorithms for things you might want to do with M+1 gram models. The first one, if I give you a sequence, how do you calculate its probability? Let's let n be the length of the sequence and m be the length of the history. What you're going to do is you're going to take every consecutive M+1 words, word I through word I plus m, and you're going to look up the probability of that last word, wi plus m, given the m words that came before. So presumably you're storing all of your M+1 gram probabilities in a data structure that gives you fast random access lookup. And now you get a bunch of probabilities, and I'm going to have you stop and think, what do I do with these probabilities after I've looked them up to get the total probability of the sequence? I'm going to aggregate them in some way. What's the right arithmetic operation? The answer, oh, I forgot one thing. I also have to look up the probability of the stop symbol given the final m words. Remember, it's really important to multiply this in to make sure that the probabilities all sum up to 1 across all sequence lengths. Okay, so I've looked up n plus 1 probabilities from my dice. What am I going to do with all these probabilities? The answer is I'm going to multiply them together because each of these events happen sequentially and conditionally independent of the others. And that's how we get the probability of a sequence. In practice, what we typically like to do is actually store the logarithms of these probabilities and then add the logarithms to get the log probability. This is important because often these numbers are very, very tiny, and with floating point arithmetic on a modern machine, you can get underflow errors. And we don't want that, so we take the logarithms, which usually give us large magnitude negative numbers, which are easy to add. Okay, now suppose I give you a set of sequences and I want you to choose one that has the highest probability. This is easy. You calculate the probability of each one using the algorithm I just gave you, and then you choose the one that has the highest probability. This comes up often when we have another component in our NLP system that can generate a bunch of candidate sequences, and then we want to have a language model weigh in and tell us which one seems the most plausible as an example in the language we're about to generate text from. Another algorithm that's useful to know is how to generate a sample from the underlying probability distribution in our language model. And this one is also pretty simple and intuitive. We start out by writing down the start symbol, which we might erase later, right? We might not actually need to know that the sequence started with a start symbol in our use case, but for the purpose of making sure we generate the sample correctly, we start with the start symbol. And then we're going to repeat until we get to a stop. You're going to pick the distribution, gamma, of the next word, given the m-word history that we already wrote down. And in the case of a larger than 1 m, where we've just written down the start symbol at the beginning, what we typically do is we pad the sequence with additional start symbols so that we have an m-word history all start at the beginning. So you select that distribution, and then you sample a word from that distribution. If you use Python, I think the NumPy random multinomial function will let you sample from it. In a lecture in person, sometimes I walk through how this kind of algorithm would work. It's pretty straightforward, but you basically are going to generate a random number and then map that random number onto one of the outcomes in this distribution in such a way that you are guaranteed to be sampling appropriately. And then you write down that word, and then you repeat and keep going until the word you write down is stopped, and then you're done. Finally, the thing we need to be able to do to use these models is train the model or estimate the model in statistics language. And I've written here the formulas for each of the kinds of m+1 gram probabilities that you might have in your model for unigram, bigram, and trigram. That's 0, 1, and 2 word histories, and then a more general one. And basically the general pattern is that you take the frequency of the engram that you observe in the data, and you divide it by the frequency of the history. This is really important because people sometimes think about this and they think about probabilities, and everybody has this kind of intuition that probabilities are proportional to frequencies, and then you relativize them or divide by something so they sum to 1. The key thing to remember is that what sums to 1 is all the words given a history. So you divide by the frequency of the history, not the frequency of all possible engrams. So for example, looking at the third line, the trigram, you're actually dividing by the frequency of the bigram history, W prime, W double prime. And this will give you the conditional distribution of the next word given the history, rather than the joint distribution, which is what you would get if you divided by the total frequency of everything. And note that for the Unigram model, that's exactly what you do. You divide by the total number of words because there's only the one distribution. And at the bottom, we have the general form, which is what you should remember. Take the frequency of the history together with the word divided by the frequency of the history. One small point before I go on. This isn't actually what anybody does with a real Engram model in practice. because this will have the effect that many things, any word that you don't observe with a given history will have a probability of 0. So what people actually do in practice when they use n+1 gram models is they smooth the distribution. That's usually accomplished by either adding something to the numerators and denominators or discounting, which is subtracting something from the positive numerators and then somehow redistributing that reserved probability mass across the things that have a count of 0. This is an advanced topic that isn't particularly important given what we use in today's NLP systems, but I'll point you to a textbook to learn more about smoothing and alternatives to maximum likelihood estimation. Okay, so what's happened since these models were originally introduced? They're quite old. They've been around for a very long time. Some of the trends that we saw maybe a decade ago or so was increasing scale as people had access to the web and larger data sets. We could make language models that were based on more and more data, and that tends to lead to more effective models for whatever use you might want to plug them into. We'll talk a little bit more about how they're used soon. So going web scale was a big win, and this was really helpful to a lot of kinds of NLP systems. It continues today. The trend is always towards estimating language models on more data, and this is generally seen as a good thing. As you go bigger and bigger, you find that implementing these things at scale gets harder, and so people came up with all kinds of cool ways to make them run faster using many machines like MapReduce architectures to distribute the computation across many nodes. And also great tricks for compressing to limit the memory requirements of a large language model. More recently, the trend has gone away from the kinds of Markov models that I presented, and I'm going to quickly review several stages of neural language modeling, and this will help us understand how things have evolved. I'm not going to go into a great amount of detail on neural language models, but this will foreshadow future lectures and future reading you might do on this important topic. So one step away from the models that I showed you was the use of convolutional neural networks for language modeling. And so here the idea is that each word is going to be treated as a vector, and the vector associated with the word is simply a collection of D parameters that will be estimated. They're just arbitrary numbers associated with the word. And what we expect when we build these word vectors is that words that have similar meaning or appear in similar contexts will have similar vectors, but not identical. And usually the dimensionality of these word vectors is much smaller than the dimensionality of the vocabulary. And so the idea is that you take your history, wi minus m up to wi minus 1, that's m vectors, but it's a fixed size. And so you can build a neural network that maps it to the vector gamma, which is your distribution over the next word. And so it's a fixed input, fixed output a neural network, and a convolutional neural net was an appealing option to get started with this idea. And there was a paper from Bengio and colleagues in 2003 that introduced this idea and found that it worked. The next stage came a few years later when people started using recurrent neural networks to condition on the entire history of n-1 vectors. And the way this works is that at each word, you define a distribution based on something called the hidden state, which is a calculated vector that depends on the whole history up till now. That hidden state is fed into a function called the recurrent function that gives you the next hidden state given the current word. And so you repeatedly apply the same function given the previous state and the current word to get the next distribution over the next word that comes next. And because this, you can trace a computational path all the way back to the very original word vector at the beginning of the sequence. There's no longer a Markov assumption. So this is potentially very powerful and was found to be a really big advance in what we could do with language models, and a whole lot of work went into the design and testing of different kinds of recurrent functions to get more and more effective generalization. More recently, just a few years ago, we saw the introduction of another kind of neural network called the transformer, And there are a number of things we could say about this. I'm not going to teach you the whole transformer in this lecture, but the key idea, I think, when I look at this model is that you no longer are really treating the history of vectors as a sequence. Instead, you're extending the vectors so that they encode the word's positions. So there's like a vector associated with being at position 4 or position 7 or whatever, and that's appended to the word vector. And so now you have essentially just a collection of vectors that can get plugged in, and the sequence doesn't matter. And so the probability you calculate for a word at a given position doesn't depend on the probability you calculated or the hidden state you calculated at the previous position, and you can parallelize all the words calculations at the same time when you're training, which is a really big win when you want to scale to lots and lots of data and use modern hardware like GPUs. So currently, the most famous language models as of this lecture in 2020 are based on transformer neural networks, and we have yet to see what the next stage in this story will be. Okay, so how do we use these sequence models? I've been talking a lot about how we build them and different kinds of assumptions, and I gave you sort of the foundational language models and then talked very briefly about how they've evolved. Once we have a really good language model, what do we use it for? There are essentially two kinds of tasks that involve sequences. One I call analysis, where your algorithm is going to read the sequence in and predict or generate something else. And then the other is a generation task where something else comes in and the sequence comes out. And of course, we also have tasks like machine translation, where the sequence is both the input and the output, and you're doing both analysis and generation. Sequence models, it turns out, are useful in both scenarios. And to understand that, I'm going to introduce a very old and important concept called the Noisey Channel. So here's the idea. In the Noisey Channel, we're going to tell a generative story about our data, and not just about one sequence, but about data that involves two random variables that one or both of which could be a sequence. So in this paradigm, we start out with a probability distribution called the source over random variable y. And so the source when the data was generated, the story we tell is that first the source model generated the true value of random variable y. And then what happens to that value is it gets passed into an object called the channel, which I like to think of as a blender that changes or disrupts or messes up that value, giving you a new value called x, a new random variable x. So the channel defines a random process for transforming a y into an x. It gives you the conditional distribution of x given y. And x is what we observe. And so what we're doing when we use this model, when we perform inference, is we're trying to recover the true y given x under the assumption that the source channel distributions are what produced both x and y together. So what we're interested in is finding the most probable y given x. Our model doesn't tell us about y given x. It tells us about p of y and p of x given y. But fortunately, because we remember Bayes' rule, we know that we can maximize instead the product of p of x given y times p of y, and it will give us the same answer because these two quantities inside my two argmaxes on the slide are proportional to each other. So the idea is that you want to pick a y that is both likely on its own and also likely to have given rise to the evidence that we observe x. So the sequence model can actually be either or both of these components. Traditionally, it was often associated with the source. So in early models for statistical speech recognition and machine translation and optical character recognition, also spelling and grammar, spelling and punctuation correction, we had a language model as P of Y, and then there was a task-specific channel model that modeled the disruption of good English or good French or good whatever language you're working in into what we can observe. In the case of speech, it would be audio signal. In the case of translation, it would be your source language, the one you want to translate out of. And then decoding works backwards and tries to recover the true value of y given what you've observed. This idea for machine translation actually dates back to the very early days of computer science and information theory, where Warren Weaver famously proposed that when he wants to translate from Russian to English, he's going to imagine that in fact the Russian speaker is thinking in English, and through the vocal apparatus of a Russian person, that English gets corrupted into Russian, and our job is to decode it back. So we call this, that's why we call this process of recovering the true Y decoding. We're working backwards to undo what the channel has done. Sequence models can also be channels, and there are many examples for things like text categorization, language identification, which is a kind of text classification, information retrieval, sequence compression, transforming questions to search queries. In these cases, usually Y is something lower dimensional, and the idea is your channel model is a conditional language model that generates text or words, often a bag of words in the information retrieval case, conditioned on that label or whatever the other desired output is, which we again call random variable Y. More recently, there's a completely different way of doing things that has emerged, and here it's much simpler. I like to teach the hard thing first and then go to the simple case. In this case, we simply have a direct model, and this is input goes in, and there's a conditional distribution of Y given X, and output is Y. And so what we're trying to do is find the argmax of the probability of Y given X over Y. So pick the most likely output given the input. This is much more closely related to discriminative models for classification, for example. And this is how most modern machine translation systems work. And you can see similar models applied to things like dialogue and text summarization. And so this, I think this way of doing things where you have a direct model is much more strongly associated with the powerful expressive neural networks that have come to dominate in the field right now. So in some ways, I like to remind people that there are many things we care about, and in some ways, engrams are kind of hard to beat. They are very fast to work with, and if you have a long markup order, I should title this, it's hard to beat M plus 1 grams, but conventionally they're often referred to as Engram models, so sometimes I slip and call them engrams. But they can fit the data really well. If you have a lot of data, you need to have a longer markup order to get a good fit, but they're really cheap. They don't require any backprop or neural net training or fancy libraries to get a basic Engram model working. They are kind of out of date. We don't see people using them too often now, but that didn't happen until we could scale very complicated models up to very large amounts of data. So basically, I don't think the neural networks, if they had been invented 20 years earlier, they would not have worked well because we didn't have the hardware or the data set sizes that we need to get them to work. So all of these things are kind of interdependent, and I think it's appreciating where we are now hinges on understanding how we got here. We do see things, we did see better systems come about than engrams when we either applied very task-specific knowledge, like we knew something about the problem and we could make further assumptions or weaken assumptions in selective ways, or we had really good domain knowledge, like we know some things about linguistics, and there were interesting results. About 20 years ago, one of the fashionable topics was to try and build language models that were more linguistically informed. So machine learning folks would call that domain knowledge. And so I think, ultimately more data would usually trump those kinds of gains, because the way we measure language modeling performance really isn't about explaining everything in language. It's really how well do we do on tasks that we care about using conventional metrics. That's a much longer discussion. We're not going to go there today. I do want to present one kind of alternative to the standard language modeling Engram story that's both historically interesting and a really nice stepping stone to hidden markup models coming up next. So this was introduced 30 years ago in 1990. It's called a class-based sequence model. The notation here is a little bit different from what's in the original papers. Let's assume that we have something called CL, which is a deterministic function that takes a word and maps it deterministically to a smaller set of classes. So every word belongs to a single class, and it's known in advance. It's already been decided before we start modeling. And in the Brown et al. Paper from 1990, they used a clustering algorithm to cluster all the words in the vocabulary into groups. It's a really interesting algorithm. People continued to study it for several decades after it was introduced, but we're not going to talk about that in detail today. The form of the model is given on the slide. So you now have two distributions. One of them generates a word given a class. So the class of every word is known. What we can associate with that class is a probability distribution over the words that are members of it. And then the second part, gamma, is a Bygreen model or a Markov model over the class of a word at position I, given the class of the word that came before. And if we can put these two things together, we can define a full distribution over words. So here's how it will work. We start out with a start symbol, and then we sample from a black die to generate the class of the first word. And say we pick 53. And then, given the fact that we just chose a class for the first word, class 53, we're going to pick a word. And we're only going to pick, the word using a die associated with class number 53. So I've colored these dice red. I pick up the class 53 die, I roll it, and I get a word. I get the word I. Notice, because every word is only associated with one class, each word in the vocabulary will only appear on one of the dice. Okay, so these are smaller dice than the Unigram dice we had before. Okay, next I'm going to pick the next class for word 2. I'm going to condition on history, which is just the cluster of the word that came before, so class 53. Sample from that die, I get class 23, and then I go to the red die for class 23 and generate a word I want. Go back to generating a class, I pick 2 given class 23, now generate a word from the class 2 die. And I repeat this process going back and forth until I eventually get to the end of the sequence with a stop symbol in the class distributions. So there's the math again. This model makes a rather different kind of independence assumption. First, it assumes that the words depend on nothing except their class. And second, it makes a Markov assumption about the classes. So each word's class depends only on the class of the word that came before, not even the word that came before, just the class. So one of the big advantages of this model is that it has far fewer parameters than your standard Markov model of the same order. So compared to a Bygreen model, which has size of vocabulary squared parameters, this model actually has much smaller. So let's say we have C classes. Let's look at the gamma part of the distribution. If there are C classes, then we have C dice, C black dice, and each one has C sides, plus a stop symbol. Multiply those together and you get C squared, order C squared gamma probabilities. If C is a lot smaller than the vocabulary, then that's a big win. The other part is the eta distribution, where you generate words giving classes. And there, remember that every word is only associated with a single class. So if you add up all the probabilities across all the red dice, you're going to get a total of the size of the vocabulary. So the total size of this model in the number of parameters is going to be C squared plus size of sigma. So it's like we've taken a Unigram model and added this extra thing to it in terms of number of parameters, and that extra thing doesn't depend on the vocabulary size. How well will it generalize? Well, if we do a good job of smoothing the class Bygreen distribution, then it should do pretty well. Notice that the size of these distributions is smaller, so we're probably going to be able to, we're probably not going to be as prone to overfitting. If we've done a really good job of choosing the classes, then this model will be able to generalize pretty nicely, as long as, again, we've dealt with the out of vocabulary problem by smoothing the word vocabulary, and probably also smoothing the Bygreen class probability, the gammas. Okay, so where we are now is that we've covered Markov models. That's all I have to say about that basic building block with connections to language modeling and NLP. The next topic will be hidden Markov models, and we'll turn to those after a break in the next video.
Okay, sorry, I was answering a question. Happy to take more or clarifications if I answered your question and didn't actually give you the answer you were looking for. They've gone quiet. This is the Lisbon Summer School I remember. Okay, the classes you mentioned regarding the Brown approach. I think I might have missed what these are, handwritten rules or something else. Yeah, so in the Brown class-based model, I didn't really go into this. I just sort of said, assume that these classes exist. They could be hand-created, but in fact, what Brown and colleagues did was they used a clustering algorithm that clustered words. And that clustering algorithm is actually more famous than the class-based model I was talking about. It's called Brown clustering. People wrote a lot of papers about it. There's the most recent thing I remember seeing was a spectral method for inferring Brown clusters. It's basically a kind of distributional clustering where you try and group words together into hard clusters based on the context they occur in. So it's reminiscent of word vectors, but instead of a word vector, you get a cluster. The other interesting thing about Brown clusters is they're hierarchical. So you get sort of arbitrary level of fine-grainedness. And people would often essentially represent the hierarchy using bit vectors, so that like one end of the vector was giving you very high level information, and the low end of the vector was giving you more detailed information about the word. A really interesting paper that came out in 2010 by Turian and colleagues considered Brown clusters alongside other word vector type representations. This paper actually won a Test of Time award at ACL this summer. It's kind of an interesting synthesis paper, definitely worth checking out if you want to kind of understand how the older clustering methods relate to some of the newer word representation techniques. Could you please once more speak about the parallelism of transformers? So basically the transformer, I'm not going to say a whole lot about this because I don't think the summer school has covered transformers. So a lot of people may be puzzled about what we're talking about here. But the transformer is a neural network, which means it takes input and it does a whole bunch of stuff that's kind of hard to understand in the middle that decomposes into a lot of arithmetic operations and then spits something out. And when transformers are applied in NLP, they typically are used to go from a sequence to either the continuation of the sequence or a label or some other kind of output. But if you dig into the equations, the really interesting thing about the transformer is that it's not really a sequence model. It's actually a model that takes a collection of vectors, and it doesn't inherently have any respect for the idea that the vectors are in a sequence, are an ordered list. It doesn't have a notion of adjacency in the network architecture itself, like a convolutional net or a recurrent net does, or any of the more traditional non-neural models I talked about today. It's really just a bunch of vectors go in. The way that we use transformers in NLP applies something called a positional vector that basically says, here's a vector that represents being in the first position of the sentence. Here's a vector that represents being in the third position of the sentence. And that vector is somehow, it's either added or concatenated, I can't remember which, to the word vectors before they go into the network. So it's you're basically saying that the positional information becomes part of the input rather than something that's observed directly by the model and respected in sort of the formula, the design of the architecture. And I think that's something that the original paper didn't really emphasize in a way that might have been useful to note. Not to be too critical, it's a great paper. But what it means is that you can do a lot of the processing in a transformer in parallel. You don't have to process the words in a particular order to figure out what you want to do with that collection and get to an inferential decision. So that's a big leap forward. And then add to that the fact that we use GPU hardware. That means that you often get a big speed up because you can parallel. Anytime you can parallelize calculations, that's a time for GPUs to shine. Could you please go back to explain the general idea of noisy channel and how it relates to sequence models? Yeah, so noisy channel and sequence models are kind of orthogonal. Noisy channel, you can understand a noisy channel model without thinking about sequences in particular. We often do in NLP because in language is sequences, but the noisy channel in its purest form just says there's a true distribution over data, over the desired output data, the version of the data that you hope to infer, and then once a piece of data is generated, before you observed it, it got garbled up in some channel, which stochastically added some noise or corruption to it or changed it in some way. And what you get to observe is what comes out of the channel, not what came out of the source. And your job is to decode back to what came out of the source, and everything else is just the application of Bayes' rules. So you have a parameterized model that you've estimated for the source distribution. You have another one for the channel distribution. If you multiply those two scores together for a given y and x, then you can reason about the best y given x by finding the y that maximizes that product of the source times the channel probability. When we apply that abstract idea in NLP, usually one or both of the components is a sequence model or a transduction model for the channel. And traditionally, the language models of the kind I was talking about were usually the source model. Although I think as I said in the lecture, they sometimes played the role of the channel in certain situations. So it's useful, I think, when you're getting into a field like machine learning or NLP, there's kind of this way of thinking that, like, here's a model and it's like its own thing and it's very discrete, and then there's this other model. And a more mature view that I'm trying to get across with some of the ways I present things in this lecture is that aspects of models can be decomposed, and there are sort of different levels of abstraction at which you can look at a technique and understand it. And so a thing can be both a sequence model and it can be playing the role of the channel or the source. And so things are actually, they can be broken down into smaller parts and decoupled. And that's really fundamental if you want to start building your own models. Okay, if we are working at the phone level, sequence of phones, then can we use the class-based model for phone level studies? Sure. I think I need more details to think about exactly how the observations and the classes would map into your problem, but yes. And I think as we move forward into hidden Markov models, you may see more parallels, and it might be useful. But I think I'd have to know more to give you good advice here. The class-based sequence model would where would the class-based sequence model locate on the spectrum mth order? Oh, this is a great question. Okay, so on the spectrum of order markup models, where 0 is bag of words and infinity is the entire history, where would class-based models go? And the person says, I guess it will depend on the number of classes, the comparison between n class-based sequence model and nth order markup models. So basically, it doesn't exactly fit on the spectrum. It's actually, in some ways, it's making a stronger independence assumption, because now the words are separated from each other by the sequence of classes. So you can't quite put it in there. But it is, in some sense, it's kind of like a Markov model. Well, I mean, it is a Markov model over the class sequence. And then you're basically saying that at some level, some of the information, whatever's preserved by the classes, is Markovian in the way we talked about before. And then some other part of the information, the part where you choose a word given a class, is 0 order, right? That part where you select the word after having chosen the class doesn't depend on anything else. It's its own die. So it's kind of like a weird mix. And there's probably a technical term that would better describe it than me saying weird mix, but it's kind of a weird mix between whatever the order of the class-based model is and and 0. It sounds like Brown clustering is a lot similar to classification and regression trees, the training procedure as well. Are they in fact related to one another? I don't think so. I think I think the way to think about, yeah, there is this like tree structure in Brown clustering that emerges because you're building a hierarchical clustering, but the tree is more a description of the relationship of the classes to each other. It's not used as a procedure to decide how to classify something. So I think in that sense, it's different. The one possible similarity is that when you build Brown clustering, at least in the traditional version, you're applying a greedy algorithm, a greedy iterative algorithm. And that bears some similarity to the way we build classification and regression trees. As I recall, you can't optimize those things perfectly. You tend to use some kind of a greedy method that's iterative. But I think fundamentally these are fairly different. Clustering techniques tend to kind of live, in my mind, they live in a rather different space than supervised classification methods. But there might be some deeper connection, but I'm not aware of it. In the Engram generative model, how can we make sure that each time the model is not generating the same sequence when starting with the same token? If we use random sampling, is it just with the first few tokens? So to be clear, when people use, this kind of came up before in another question, when people used Engram models, they generally did not use them on their own to generate sequences. Me doing that in this lecture was something we used to do kind of for fun to teach why these models were kind of only a poor approximation. The idea that you would just take a language model and generate sequences from it by randomly sampling was something nobody did in NLP until very recently, when the neural language models started getting really good. And this is very related to the Noisey Channel, right? We used to use these Engram models in Noisey Channel settings where there was something else weighing in to decode, not in a direct model where you simply sample from the language model and hope to see something good. So this question it's not really something we did. We wouldn't have worried about regenerating the same sequence because we didn't use the models that way. It feels kind of weird to say that we could have done that, but they just weren't good in that way. I mean, again, it was you saw the crappy sentences that they produced, particularly with small Markov order. So that just wasn't really a use case until recently. Now that we have neural language models, and I was answering this question for somebody else, we have these issues with repetition and lack of diversity, and people are coming up with all kinds of ways of altering the training or the decoding to improve over that. This was not something we worried about before because we were not using language models on their own like that. Hijacking the question about the spectrum. Given that at least some language models like transformers drop the Markov assumption, where are language models and sequence models today? Right, so it's true the current models basically drop the Markov assumption. You could argue that because they still only look at finite length sequences, they haven't completely dropped it, but for all intents and purposes, we're not thinking about language modeling in terms of Markov assumptions anymore. So for the famous language models that are being used and that are getting all the press, the GPT-3s of the world and those kinds of things, they look very different. And so the sequence models I'm talking about today they just don't bear much resemblance. The sequence models I'm talking about today are, I think, more important to understand from the perspective of building up to more complex models over complex data. So if you can understand sequences and how you might build compositional models that process sequences and and understand where the limitations come in and where how they differ from the latest and greatest fancy techniques, then you're in a better position to make use of these ideas in moving the field forward. So you know, I tend to think that a deeper, fuller understanding of the things that came before will be more beneficial in coming up with creative ways to improve over what we have now. I think one thing I would add is that the models that we have today are extremely computationally expensive. They are far beyond the reach of many people doing research and development in these settings. And so I think if you're in a resource constrained setting where you don't have massive machines or massive amounts of data, for example, you're working on a language that doesn't have corpora anywhere near the scale of English, then you're very likely to want to go back and reconsider some of these older techniques that maybe play better in the small data setting, the low resource setting, and definitely won't blow your entire budget on computation. So I think there are a number of good reasons to be kind of familiar with these older, more straitjacket restricted models that they can't do all the things the new models can do, but there are some reasons you might want them to not be able to do those things. Are current neural language models strictly better than engrams for any context setup and target word? E.g., are there some types of tokens to predict that are better predicted with an engram, or are there some context windows that lead to better next word prediction using an engram model than an RNN or transformer? This is an interesting question. I'm not sure I've ever thought about it in that way. I tend to think about it more as the context of the data, the compute power, the task you're trying to perform, and those kinds of constraints that come from the problem you want to solve. Then there are various trade-offs you can think about among the different kinds of models. But I don't think I've ever seen an analysis around like particular types of tokens or particular types of contexts. That's an intriguing question. I don't think I have a good answer. Moving over, there's something in the chat.
We should probably move on because
we should move on. Okay,
yeah,
I will mute
late.
and we will go to the next chunk. All right.
Okay, continuing where we left off, we're on the third part of the sequence models lecture, and we're going to start talking now about hidden markup models. So a hidden markup model, or HMM, is a model over sequences of symbols like we had before. But now in this model, we assume that there's some missing information associated with each symbol in the sequence, and it's called its state. And so the states are discrete. We assume that there's a finite set of possible states. I'm going to use lambda to denote that set. And the way we define the distribution of a sequence of symbols together with the sequence of states. So notice here I have P of start, S1 and W1, S2 and W2, all the way up to Sn and Wn, and to stop at the end. The probability of that double sequence of states and symbols is given by the formula on the right. So this should remind you very much of the class-based language model that we saw in the last section. You have an eta distribution over symbols or words given states, and you have a gamma distribution, which is here a bigram or markup distribution over each state given the preceding state. So again, it's a joint model over the observable symbols, the W's, and their hidden or latent or unknown classes or states. And I'll probably use those terms class and state interchangeably in this lecture. So to visualize how the sequence gets generated, we have, just like with the class-based model, we have black dice, one next class die per class. These are the gammas, and we start by writing down a start symbol and then generating the next class. Say we randomly pick C53 by rolling the start die. And then we switch and we go over to the red dice, where we have one per class or state, and they have words written on the side. And so we roll the class C53 die, and we come up with a word. The only difference between the class-based model that we had earlier in the last section and this model is that now the different dice can share words. And so every word could potentially be written on every die. And so when you see a word, you don't automatically know which class it's associated with or which state generated it in the HMM language. And then we go back to the black dice, and we pick up the history equals C53 die. We roll it, and we get, say, C23. We pick up the C23 red die. We roll it. We get a word. We get want, and we repeat. We alternate between black and red, generating transitions and emissions as we go. So that's the technical language used for the black dice is transition from state to state, and the red dice is an emission from a state. We emit a word. And there are really two ways you can talk about it. The way I showed it is you alternate between black and red, transition, emit, and so on. The other way to think about it is that first we generate a sequence of transitions and write down all the states, and that's just a markup model on the classes or the states. And then we stochastically replace each class with a word. And so then we roll a red die for each of the black dice that we generated. Both of these are equivalent and give you the same math and the same algorithms and everything else. So remember it the way that makes the most sense to you or feels the most intuitive. Just like with Markov models, we can generalize HMMs to have higher Markov order, and we do this by changing the gamma distribution to condition on more than one preceding state. And so you see here a sort of generic mth order HMM. The eta is the same, but the gamma now conditions on more history. The number of parameters is going to grow as we increase the history length, just like it did with Markov models, exponentially in the size of the state space, lambda. Because the state space is usually much, much smaller than our vocabulary, going to higher order Markov models is generally not going to be as expensive as it was for higher order language models. So, sorry, higher order HMMs will not be as expensive as higher order language models were because we have so many fewer states than we have words in most use cases. And the benefit of doing this, of course, is that now you have longer memory and the words are effectively influenced by longer and longer histories, although only through the current state. So you still have kind of a capacity limitation that comes from the number of states that you put into your model. I'm going to stick with first order HMMs today because they make all of the notation a lot easier and they give you all the intuition you need. But everything I say will generalize to higher order HMMs, and mostly that'll be left as an exercise. Okay, so I want to talk a little bit about how HMMs have been used in NLP and talk about some sort of classical use cases. You'll notice the years on the paper cited on this slide are a long time ago. HMMs are not the state of the art for solving any of these problems now or speech recognition, and they've probably also been replacing computational biology, although I'm not completely sure about that. But again, it's useful to understand how we framed these problems using HMMs because some of the machinery that we get from hidden Markov models, some of the algorithms, can still be used today, even though we learn the parameters of our models rather differently. So part of speech tagging is sort of a classic NLP task where words are labeled with parts of speech that come from linguistic theory of syntax. Shown here is an example where the parts of speech are drawn from a collection defined for a data set called the Penn Tree Bank, which is a syntactically annotated corpus from the early 90s. The codes here are not important to remember. The word classes or parts of speech that are used should be pretty familiar to you. The Penn Tree Bank part of speech tag set has about 40 tags. And they're things you probably have seen, things like adverb, determiner, adjective. They're a little bit more fine-grained for things like verbs, nouns, and punctuation to capture the fact that English has a different surface form when a noun is plural versus when it's singular, or when a verb is in the progressive form, like ending in ing, like paying, or in the present tense form, or the past tense form like VBZ. VBZ denotes for the word was here in this example. There are also parts of speech for punctuation symbols, which is not conventionally done in linguistics, but it's done in NLP because we see punctuation and we want to treat it like symbols or tokens, just like words. We can't really ignore we can't really ignore punctuation when we're doing NLP. So this example just shows how a linguist might tag the words in this little example sentence, and so that's sort of one example of using an HMM. Traditionally, the idea would be that each word was generated from a state corresponding to its part of speech tag, and each part of speech tag was generated conditioned on the preceding tag. So in this use case, typically the POS tags are equivalent to the states. If you go to higher order Markov, higher order HMMs, then the states will correspond to the preceding pair of tags. And so you'll have size of tag set squared states. I think typically POS tagging with HMMs used up to trigram models. So in that case, I guess your preceding state would have been 2 tags, and each tag would be generated conditioned on the preceding 2, like in a trigram model. Another problem, this one's still actively researched, is named entity recognition, where we have text and we want to identify spans of text that correspond to real-world entities or that refer to real-world entities. We often call the sequence of words the mention, and the entity is not the thing in the text, it's the thing outside in the world that the mention refers to. So in this sentence, I've highlighted in colors 3 different entity mentions, and then we can label them in sort of with 2-part tags. The first part is a B, I, or O. O means this word is not part of any named entity mention. B means this is the first word in a named entity mention. And I means this is another word, but not the first one inside of a named entity mention. This is a nice scheme called the BIO tag scheme for identifying spans that are contiguous. And what's nice about it is that you can tell when 2 spans occur right next to each other, which doesn't happen in this example, you can tell the difference between one very long span and 2 spans that just happen to be adjacent. The other thing that we add, the other part of the tag for B and I tags is the type of the named entity. So in this example, we have 3 types. We have person, space shuttle, and place. This is not a conventional use case. Space shuttles don't usually have that much importance in NLP. I made that one up. A conventional named entity recognition data set uses person, place, organization, and maybe a small number of others. But you can define whatever types of entities make sense in your application. The reason this task isn't completely trivial is that the way that we name things, particularly in English, and especially in American English, we like to name things after other things. So Kennedy Space Center is a place, but it's named after Kennedy, who was a person. And there are many examples of this. So, I teach at the University of Washington, which is named after a person, George Washington. But we also have many examples of places named after other places, or people named after places, or organizations named after people. And people, it goes in all directions. So this gets you have to have some background information or knowledge in order to do well on this task, or see a lot of training data. Anyway, that's a second example. A third, this one comes up in machine translation, where we want to learn a model to translate from, say, German to English. In this example, I'm showing you an instance of data that's of the kind that's used to build machine translation systems. It's called parallel data. We have 2 sentences that have essentially the same meaning in the 2 languages, German and English. And in some early work in data-driven machine translation, we would make the assumption that each of the words in one of the languages was generated from one of the words on the other side. And so in this case, I'm drawing the arrows to go from German to English to indicate that each of the English words was produced because it corresponds to a particular German word that was sort of central to the choice of the word that came next in English. And so these arrows are often called an alignment or a correspondence. And there were many different models for word alignment, but one of them was the hidden Markup model. And the idea is that the words in German are states. And when we go to a state, we can generate a word, and then we can, like Mr. here, and then we transition, and you can always transition in this model back to the same state. So you can go back to null, and then generate president, and then go back to null, and then generate comma, and then go to Noah's and generate Noah's, and so on. And so the HMM model for word alignment was a very successful approach to modeling and inferring the links between the words in 2 parallel sentences, which was an important stepping stone to building statistical machine translation systems. We don't really use this model directly in state-of-the-art machine translation today, but you can see it kind of echoing in the notion of attention, where words, as words are being generated on the target side, the neural net is said to attend back to words on the source side, kind of like an alignment. Okay, so those are some use cases some classical use cases for HMMs. If you want to keep 1 or 2 of them in mind as we go forward, sometimes a concrete example is helpful. But to reiterate, an HMM is a model over sequences of symbols. And we assume that each symbol is associated with a missing or hidden state that's not known when we're doing inference. The model defines the joint distribution over words and states, and so this is a pretty big departure from our assumptions in the earlier part of this lecture, where there was nothing missing. The data was just what we could see. It was just the words, and each word was generated conditioned only on other observable information. This change has a lot of implications for the algorithms that we might use to work with this new model. And so what we're going to do next is talk about algorithms. And here's the list of algorithms that we're going to cover in the remainder of the lecture. And the first one is probably the most important one and the hardest one, hardest hurdle to get over once you understand the algorithm that we use to calculate the most probable state sequence. Everything else will be relatively easy. So that's going to be our main focus next, is if we have a sequence of words, how do we find the most likely state sequence that goes with those words under the HMM? Okay, so to be a little bit more formal, the input here is an HMM, which means our probabilities gamma and eta over transitions and emissions respectively. And we get a symbol sequence W. And what we want to do is find the S sequence, the state sequence, that is most probable given the words and the model, the HMM. So that's what I've written here in math, the argmax over all possible S of P of S given W gamma and eta. In statistics, we call this a maximum a posteriori inference problem. We're trying to find the state sequence with the highest posterior probability. And from a computer science point of view, what we're going to solve here is a discrete combinatorial optimization problem. What we're choosing is a hard sequence, right? We're going to pick one state for every word, such that the total probability of the sequence is maximized. To make this a little concrete, I'll use POS tagging. So here at the top, I have W, my sentence. I suspect the present forecast is pessimistic. And then what I've written down in a column under each word is the set of part-of-speech tags that are attested in some training data from the Penn Tree Bank for each of these words. And some of these may be a little bit surprising to you. That could be because there are POS tagging errors in the data. It could be an unusual use of the word. It's interesting. It's always interesting that the can be a noun. This might be a reference to the long forgotten 70s rock band, the. I'm not sure. Maybe a little bit more realistic is the word suspect, which when I say it like that, it's probably a noun or an adjective. When I say suspect, it becomes a verb. One of the interesting things about English is that sometimes we change the pronunciation of a word depending on its grammatical function. So whether it's a verb or a noun might depend on the pronunciation, but in the text, we don't have the pronunciation. All we have is the remainder of the sentence. Anyway, so even if we assume we know which POS tags are conceivable for each of these words, if we multiply out all the possible options, there are, for this short sentence, 4,000 possible state sequences that we could choose. And they're not all equally probable because in English, we have grammar. We don't usually put determiners right before verbs, for example. That pair would be incredibly unlikely. And so we want to use that kind of statistical information about what sorts of sequences of POS tags make sense alongside the probabilities of each of the words being associated with each of the tags. And that's essentially what the HMM will do to make this decision. So let's talk about, like I said before, I like to start with naive, simple solutions to make sure we aren't missing something obvious and understand why the problem is a little bit more complicated. One thing we could do is just list all the possible label sequences of the right length for the sentence, score them all, and pick the most probable. This is correct. This is going to get you the right answer. It's if you implement it correctly, which probably is not too terribly hard, you can do it. But it's incredibly inefficient, and it's not going to work nicely for very long sentences at all because it's exponential in the size of the label space. Another thing that people are sometimes tempted to do is to start at the left edge and use the HMM probabilities to choose the most probable state at position I, given the previous state and the current word. Essentially, you'd be multiplying together the transition probability of SI, given SI minus 1, with the emission probability of WI, given SI. And then you just work left to right. The problem with this, and you know, this is probably not the worst thing you could do, but the problem is it's not actually correct. You might actually get a solution that isn't equal to the most probable sequence. And the reason is that you're ignoring right to left information. You might make a choice about the seventh word's label, and then when you see the eighth word, that completely makes that choice untenable, but you can't backtrack and change it. So while this is very fast, it's linear time and very efficient and tempting, it's not correct. So I'm not going to tell you never to do anything like this. Something like this, maybe with a little bit of management of alternate hypotheses, leads you to a technique called beam search, which is quite reasonable and widely used in NLP today. There are situations where doing something like this is probably fine, but for the purpose of fully understanding the model, I want to talk about a solution that's both efficient and correct. Will give you the optimal max label sequence. So here we go. So when we look at the model and we look at the set of choices that we need to make, one of the key intuitions you should have is that each word's label depends really on two things. It depends on the word, of course. So looking at my example here, the word forecast, obviously, knowing that the word that we're labeling is forecast should influence our choice of the label. But it also depends on the labels next door, which of course we don't know when we're starting out, right? That's the challenge, that these labels interact with their neighbors, but they only interact with their adjacent labels in the HMM. They don't interact with all the other labels in the sequence. And so, you know, in this little diagram, what I'm showing you is if I only had one piece of information, like the label to the left or the label to the right or the word, I might make a different choice. So, for example, if the label to the left is known to be adjective and I know nothing else, I'm probably going to pick that the next word is a noun. But if I know that the previous word is an adverb, RB, then I'm probably going to want to label the word a verb. So each of these different, you can think of each of these different pieces of information, known or unknown, the word, the preceding and the succeeding labels, as sort of weighing in on the decision. And somehow we have to mediate between all of them and make all the decisions all at the same time. Okay, so the way we're going to solve this problem is to think about the choice first at the very end of the sequence. And I'm going to introduce some notation as I go. So when I think about the very last word in the sequence, I notice there are three pieces of information that might influence my choice. The first one is the word, of course. The second one is the label of the word to the left, which of course I don't know. So we could call that S sub n minus 1. But we don't know it, keep that in mind. And then the third is the fact that we're at the end of the sequence and the next thing that happens is a stop. Right, the last thing after the last state is generated is we go to a stop state and stop generating. So these are the three pieces of information, and the reason we like to start at the end is that two of them are known: the stop and the word, the nth word, are known, but we don't know again what Sn minus 1 is. If we did, then we could score every possible label sigma for the last word by multiplying together three things. The probability of transitioning from sigma to stop, the probability of emitting, I should use my pointer here, so that's the probability of transitioning to stop given sigma, that's a transition probability, the emission probability of generating the nth word given sigma, and then of course the probability of transitioning from the preceding state, Sn minus 1, to sigma. If I knew the score of every sequence up to n minus 1, then I could easily choose the last symbol. But I actually don't care about the whole sequence up to Sn minus 1. I really only care about the choice of Sn minus 1. That's all that that's the only thing that matters. In my previous slide, in my diagram here, notice that I don't care. I don't have to know or care what any of the labels are for the preceding words before word n minus 1. Okay, so what I really need is to know the score of the best sequence that ends in each Sn minus 1. So if I had that, if I had a value for each preceding label, if I had pre-calculated that, then I could make my choice about Sn. So I want you to think about that sort of best prefix score for each possible choice for the preceding label as a pre-calculation that's going to happen first. And then once I've done that, I can make my choices. So here's the interesting thing. This is essentially the formula that I would have if I knew the score of the very best sequence ending in at word n minus 1 for every possible label. So call that score sub n minus 1 of the label or state sigma prime. So the choice for the score, the choice for the label at the last word would be to maximize over this score at the last word, score sub n of sigma, choosing the sigma that gives me the highest score. And again, there's going to be 4 pieces to this now. The first one is the transition. We know that we had to transition from this last state to stop. We know that this last state had to generate word n. And then what we're choosing among is preceding labels, which transition to sigma, and which each on their own have a score corresponding to the best label sequence up to that point. And so this now gives us a recurrence. So there's one score for each possible last state of the prefix at each position. So how do we get score n minus 1? Well, we do exactly the same thing, only now we depend on the score at position n minus 2. Notice that in this recurrence, the stop transition only happens at the very last stage. So things get a little bit simpler at position n minus 1, which depends on emitting word n minus 1, transitioning from some preceding state, sigma prime, and the score of sigma prime being the last state for the prefix of length n minus 2. That score in turn depends on, in the same way, on the score at n minus 3, and so on all the way back to the beginning. And at the very end of the recurrence, sorry, my pointer's not going, the score at position 1 is very easy because we know that the state that came before position 1 is the start state. So here we can calculate, in the base case of the recurrence, we can calculate the score of a label for the one length prefix of the first word by multiplying together the probability of transitioning from the start state to that label and the probability of that label generating the very first word. So this recurrence is quite elegant. It's a little different at the beginning. It's a little different at the end. The key is that we can calculate score 1 without depending on anything else. And then using that, we can calculate score 2. And using that, we can get score 3. And so the Viterbi algorithm does this pre-calculation of the scores by working from left to right. So here's the first part of the algorithm where we generate these prefix scores. We calculate score 1 by simply plugging in the appropriate etas and gammas. That's the top line here. And then we work from left to right, and we move I equals 2 to n minus 1. Consider every possible label as the last label in every prefix. So the runtime of one step of this middle part is going to be we're going to calculate a score for every label, and for each one we have to do a little max over the preceding candidate labels. So the runtime of this one little step is going to be quadratic in the number of labels or size of lambda. And then the last step is just a little different because remember we have to multiply in that stopping probability, the transition from each sigma to the stop state. Okay, so those are the scores, and my claim is that if I do all this calculation and then I ask for the max score in the very last column, score sub n, across all labels, that will be the highest joint probability of states together, of any state sequence together with the words that I've observed. I am not going to walk through the proof. I'm simply going to show you a high-level sketch of how this comes to be the case. The way we get to a proof is by iteratively plugging in the formula for each of the scores. So we start by plugging in the formula for score sub n, and it depends on score n-1. We plug in the score for at column n-1, and that depends on the score at column n-2. And we keep doing this, and what you see unfolding across each line of this this nasty formula is that each time we sort of expand out a max product kind of formula where there's a max and then a product and then a max and then a product and then a max and then a product. And so at the very end, you have this really long, n-length max product nested formula. And because of distributivity of product over max, you can move all the maxes out to the left. And that brings you back to the total probability of the two sequences given the HMM. I'll leave this up for a moment so you can contemplate it and try to absorb the key idea. The Viterbi algorithm is sort of the first instance of a larger family of methods called max product algorithms, because they do exactly this kind of expansion, or they exploit this kind of expansion and sort of rearrange the calculations of max and product operators to be efficient. If we carried out the Viterbi algorithm on our little example, we might see something like this. Notice a couple things. Because I pre-selected which POS tags were allowed for each word, there are a number of empty entries in the table. Those default to a value of 0. And then I also want you to notice that as I move from left to right, the numbers get smaller and smaller and smaller and smaller. This is one reason we usually use log math when we implement algorithms like Viterbi, because we don't want to have underflow as we get to very long sequences. Okay, now I haven't given you the full Viterbi algorithm. I've only given you the calculations that let you get the probability of the best label sequence. But that's just a number. We don't actually care what the probability of the best label sequence is. We care about getting the best label sequence. So what we need to do is use the scores to recover the actual symbols, the S1 through Sn. And so here's how it's going to work. Remember that the score at position I of a label sigma is the score of the best label sequence up through the ith word, ignoring everything that comes after. So that formula, I think this is the first time I've actually spelled out what score sub I is in terms of probability. It's the probability of the joint probability of the first state, the first word, the second state, the second word, all the way up to the ith state being chosen to be sigma and word I. And all the preceding states are the most probable ones up to this point if the last choice is sigma. This is a similar trick to what we used before. If I know what Si+1 is now, then I can use it to choose which Si got me to that Si+1. And so the trick here is to keep a back pointer. Every time I make a max choice in calculating one entry in the table, I'm going to remember what was the argmax of that choice, and I'm going to keep a pointer back to that preceding cell that got me to the argmax. So this is kind of a messy visualization of what that might look like, but you can see from any cell there's one arrow going back to the preceding column. And so the intuitive idea is once I get to the end, pick the max in the last column, I'm simply going to walk backwards and follow the arrows to get me a path back to the beginning, and each step along the way will tell me what label I should give one word, working right to left. So these are the choices I would have made, and now I have my label sequence corresponding to which row is chosen in each column. So here's the full algorithm with the scores and the back pointers. For every label, I'm going to first calculate the score at position 1. I don't need a back pointer here because this is the last thing I'm going to get when I walk backwards at the end. Then for each max step that's taken in the middle, I'm going to keep a back pointer that's simply the argmax of the thing inside the max formula there. And then this repeats all the way up to the last column. And again, we keep a back pointer in the last column, just like before. It's the argmax to the max expression just above. After I'm done calculating all the scores and back pointers, I start by choosing the last symbol that maximizes the score. And then in general, I'm going to let the label at position I-1 be the back pointer from the label I chose at position I, and I work back to the first word. This is another example, a classic ambiguous sentence, time flies like an arrow. This is a nice illustration for why POS tagging might be useful. This sentence is, it's sort of got a metaphorical meaning that most people interpret right away. Time flies like an arrow means that time flies fast. But there are a couple of other readings, and one of them, I think it was Groucho Marx told a joke, time flies like an arrow, fruit flies like a banana. So basically, he's sort of like, it's a play on words where now time flies is a compound. There are these flies, they're called time flies, and they have an affection for arrows in the same way that fruit flies have an affection for bananas. Definitely not the original intended meaning. That's why the joke is kind of funny. Notice that the two readings correspond to different POS tag sequences. So when we say time flies like an arrow metaphorically, the verb is flies. But when Groucho says time flies like an arrow, fruit flies like a banana, the word like becomes the verb. So when we run the Viterbi algorithm, here are my back pointers with the standard HMM, you can see that the choice here of the verb is actually going to be flies. So the metaphorical reading is what's chosen. Time is a noun, flies is a verb, and like is, I guess, is a preposition. Or sort of a prepositional like word, I guess. We will leave the linguistics debate for another day. Okay, so that was the Viterbi algorithm, and it probably reminds you, if you haven't seen it before, of other algorithms. It's an instance of something known as dynamic programming, where you build a data structure that's like a table, and you store partial quantities, and you reuse each one many times. And so dynamic programming has sort of a couple properties. One is that the best solution to one problem relies on best solutions to similar looking subproblems. So getting the best solution for a prefix at position I relies on getting the best solutions to smaller subproblems for prefixes of length I-1, and so on and so forth, back to the very beginning. This is called optimal substructure. The other property is that each of these quantities that we calculate gets reused many times. So when I'm filling out the table left to right, every value in a particular column will be used to calculate every value in the column to its right. Viterbi is one beautiful example of dynamic programming. If you've ever looked at string edit distance algorithms, the algorithm for Levenshtein distance is also dynamic programming. There's a view of Dijkstra's shortest path algorithm that's like that is a dynamic programming algorithm. In fact, there's you could use Dijkstra's algorithm to solve the labeling problem with HMMs. This is a representation of the set of label sequences that the HMM allows that cast it as kind of a best path problem. So the idea is that each word has a set of vertices associated with it corresponding to the possible labels you could choose for it. And there's a start vertex at the left and a stop vertex at the right. And what you're doing when you run the Viterbi algorithm is you're scoring the edges in this specially constructed graph using the transition and emission probabilities, and you're finding the best path through the graph. You could apply Dijkstra's algorithm to do that, and maybe in some cases that would make sense. When you use the HMM, you're exploiting the special structure that this graph has. Notice that the vertices are organized into these columns, and they transition only to vertices in the next column to the right. You can't move anywhere at all. You can't go backwards. You can't self-loop. So the Viterbi algorithm can be seen as kind of a special case of a graph best path algorithm when the graph has this structure. Finally, I want to close this part by quickly analyzing the asymptotics of the algorithm. The main thing you're storing, apart from the HMM itself, when you run the Viterbi algorithm, is the table. The table had n columns, one for each word, and one row for each state or label. So the total memory requirement is n times size of lambda. And then the runtime, if you recall, you have to fill in each cell. And each cell requires a max over lambda elements, size of the state space elements, because you're considering each of the preceding words labels, possible labels, when you fill in a particular cell. So you multiply the size of the table times the number of operations per cell, which is lambda, and you get n times size of lambda squared. So this is nicely polynomial. It scales well with the length of the sequence, not so well with the size of the state space. Okay, and that was the Viterbi algorithm, and this is a good time for a pause. See you soon.
Okay, guys.
So I think this is the coffee break, right?
Yeah. Yeah, this is the time for coffee break. Noah has been answering the questions during the talk, so maybe we should take like 20 minutes break until 1920, and then come back and okay.
Okay.
If you agree, okay. See you in 20 minutes.
Okay, picking up where we left.
Sorry, didn't realize you were waiting for me. You should just go ahead.
Okay.
And just one quick thing, but because we want to try and finish close to on time. I know it's late in where a lot of people are. We'll try and keep the question periods a little shorter, and you should feel free to ask questions in the Q&A at any point. I'll try and get to them as we go. I already know the content of the lecture, so I'm happy to answer questions in parallel.
Okay, picking up where we left off, we've been talking about sequence models and specifically hidden markup models. And in the last segment, we introduced the Viterbi algorithm for finding the most probable sequence of states given a sequence of observations under the assumptions of the hidden markup model. Now what I'd like to do is turn to some, well, let's quickly recap the Viterbi algorithm. So if you recall, the algorithm has two parts. In the first part, we calculate prefix scores. That is the score for every prefix of every length, for every prefix of every length of the input sequence, ending in every possible label or state. We calculate the score of the most probable path ending in that state up to that length. So we start with length 1, and that has a closed form using the emission and transition probabilities. And then we use the preceding prefix lengths at I-1 to calculate the prefix scores for all symbols ending at position I. And we do this iteratively going from left to right. Every time we calculate a score, we also calculate a back pointer that tells us which state gave us the max in that score calculation. So this is the argmax over preceding states. At the end, we do something slightly different, incorporating a stopping probability. And once we have all of these calculations done, we follow the back pointers back to the beginning, and then we get our labels. It's important to remember that we don't know the label for any symbol in the sequence until we've done the entire pre-calculation and gone entirely from left to right. We can't know anything until we do the backtrace. Okay, so the Viterbi algorithm solves one inference problem for hidden markup models. It gives us the most probable state sequence for a set of observations, sequence of observations. But there's a whole bunch of other things we might want to do. And so I want to work through, in this segment, I want to work through more of these kinds of questions that we can answer with a hidden markup model. So the next one is the probability of the word sequence given the model. So this is kind of an interesting quantity because it relates back to language models. So remember at the very beginning, we talked about Engram models, markup models without the word hidden in them, that give us the probability of a sequence of words. It turns out a hidden markup model can be used as a language model when we want to compare sequences to ask which one is maybe most probable. Later on, when we do learning, this might inform how we learn the parameters, the gammas and the etas, the transition and emission probabilities for an HMM. But for now, let's just imagine that we want to use our HMM as we would any other language model. So here's the interesting thing to say about this. This problem turns out to be fairly easy once you understand the Viterbi algorithm. This is one of the beautiful things about HMMs. On the right side of this slide is the problem we want to solve, the total probability of all state sequences producing this particular word sequence W. In order to calculate the marginal probability of the words, we have to consider that they might have been generated by any state sequence that gets non-zero probability. So really what we're doing when we calculate this probability of the words is we're summing over all possible joint probabilities of state sequences together with these words. This is called marginalization or summing. And I want you to notice that this, if you squint your eyes a little bit, this formula on the right looks kind of like what we did with Viterbi. Finding the most probable state sequence was kind of the same thing. We considered all possible probabilities, joint probabilities of different S's with W, but instead of summing, we maximized. So we were optimizing, we were finding the single most probable sequence. We said that this was a combinatorial optimization problem and showed how to solve it in polynomial time. On the right, the problem we're trying to solve now isn't an optimization problem, it's a summation problem. but it's also solvable in polynomial time. And we use essentially the same kind of trick that we used in the Viterbi algorithm. So here's the idea. The sum of all label sequence probabilities is actually, you can break it down a lot of different ways, but one way to break it down is to say, well, whatever the preceding prefix of states is for every sequence, there's always a final state. There's always a state for the nth symbol, the last symbol in the observations. So let's decompose the sum over all possible state sequences S1 to Sn into two parts. One is the sigma at the very end for Sn, and the other is all the prefixes, S1 up through Sn minus 1. So when I break this down into two parts, here I've got the sum over the very last symbol's state, and here I have the sum over all the other symbol states, and on the inside I have the joint probability. I'm going to call this inner summation the forward probability, which is the sum of all possible state sequences that end in sigma at position n. Okay, and if you squint your eyes, you notice that forward probability can further be decomposed once again into a sum over the probability. Over the second to last symbol. We'll call it sigma prime, and the n-2 preceding states. So basically, what we're going to do is we're going to unfold this summation. By the way, notice that when we do that, we have to pull out this last bit of the, or we optionally can pull out the last bit of the formula and move everything relating to sigma, the very last symbol, out to the front. So regardless of what the prefix is, the last piece of the product, if we unfold this joint probability, is going to involve transitioning from sigma to the stop symbol and emitting the last word wn from the stop symbol. So we can pull those out to the front, and then we can treat the sum on the inside over the remaining states from 1 to n-1 as a single thing, just like we did before. And so what we're going to do is we're essentially repeatedly pull out some of the transition and emission probabilities one at a time and unfold the sum repeatedly one position at a time. So what we ultimately get is a sum of products of sum of products of sum of products. And what we're exploiting is the fact that multiplication distributes over addition. I'm not going to work through this all the way in detail, but essentially, because it's essentially the same as what we saw in the Viterbi case, the only difference is that we're dealing with a sum operator instead of a maximization operator. So this is called the forward algorithm, and what it's calculating are all the forward probabilities. So again, the forward probability at position I of symbol sigma is the total probability of all label sequences up to position I that end in state sigma. So we start with the forward probabilities at position 1, which have a closed form. In fact, they're the same as the Viterbi scores. You're simply multiplying together two things. The emission and the transition for the first word given the particular state you're interested in. Having done that for every state at position 1, we use the recurrence to do it at position I, going from 2 to n-1. And then we do a little bit of extra work, including a stop symbol transition or stop state transition at position n at the very end of the sequence. And the claim is that if I sum up over all the forward probabilities at position n across all states sigma, then what I get is the total probability of the words summing over all states. I've marginalized out all the state sequences. A slightly different view of the forward algorithm is, again, using this kind of graphical view of what we're reasoning about when we choose a state sequence. You can imagine this graph that has to start in the start state at the left and end at the stop state at the right. Each node in the middle corresponds to the choice to label a particular word in the sequence with a particular state, proceeding from the beginning of the sequence at the left to the end of the sequence at the right. So any path corresponds to one particular state sequence for the words. And what we're doing is we're summing up the scores of all the paths. Rather than choosing the best one, we're finding the sum of all of them. Path sum problems are kind of interesting. They can be written in yet another way. You can write down all the equations for all the forward probabilities, and if you squint your eyes and look at them, you notice that this is actually a linear system. That is, each f term is defined as a linear function, or I guess I should say an affine function of other f terms. So you have size of lambda times n free variables, all the forward scores, and you have the same number of equations. And so, as you may remember from math class, a linear system like this can be rewritten when it has the same number of free variables and equations as a matrix inversion problem. Nobody, to my knowledge, ever practically solves the forward probability problem for HMMs using linear systems and matrix inversion, but it's interesting to notice that in theory it could be done. It's not the most efficient way, just like using standard path sum algorithms might not be the most efficient way, because this graph has a special structure, a special lattice structure. Okay, so the forward algorithm that we just learned is a pre-computation of these partial sums from I equals 1 to n, and each one is a set of lambda quantities, the column, and each one is a sum over lambda combinations from the column before. So the asymptotic analysis ends up being exactly the same as Viterbi. The runtime will be size of lambda squared times the length of the sequence. But interestingly, this choice to go from the left to the right is kind of arbitrary. And in fact, you could start at the right end of the sequence and do something very similar, working from right to left. And in fact, that algorithm is called the backward algorithm. I'm showing it here for completeness. I'm not going to walk all the way through it. Notice that it starts at n. There's a closed form for the backward probability at position n, and then it works right to left. And if you sum over the last column corresponding to the first position in the sequence of the backward probabilities over all states, then you get the same quantity. So this is two ways to get exactly the same quantity. One starts at the left and works to the right. The other starts at the right and works to the left. And they're really just two different ways of rearranging these sums of products of sums of products of sums of products. And they're both called, in a more generic analysis of these algorithms, they're known as sum product algorithms, unsurprisingly. Of course, the intermediate quantities are different. The forward algorithm thinks about prefixes. The backward algorithm thinks about suffixes. So here's kind of a thought experiment. We had two ways of calculating this summation of this summed quantity, the probability of the words, corresponding to the forward and backward algorithms, corresponding to different arrangements of the terms that you need to get the value you want. Continuing the analogy to Viterbi, which is really the same, just using a max instead of a plus operation, could we have an algorithm that goes from the right to the left and uses the max operator, and would it give us the same solution as the Viterbi algorithm? Would it give us the most probable label sequence for the words? I'll let you think about it for half a second. And the answer is yes, because we're using essentially the same distributivity property in both cases. And this kind of distributivity property leads us to an even more general view of these algorithms that I think is worth knowing about and is kind of fascinating to think about. So here's the thinking. The Viterbi and the forward algorithms are essentially the same algorithm. They're the same kinds of calculations. The only difference is sort of like which mathematical operator do you plug in at the bottom level? Is it a max or a sum? So if we consider them being the same abstract algorithm, you can just think about that choice of which operation you use as kind of a parameter of the algorithm. And there's a term there's sort of a larger statement you can make about what kinds of operators will work in the way that we want to give us an interesting quantity. And the key thing is that we have to choose operations that form a semi-ring. So a semi-ring comes from abstract algebra. It's a set of values and some operations that obey certain properties. And I'll try to explain briefly what they are and how they map onto the two things we've seen, and then we'll talk to some other cases that are kind of interesting. So the set of values in a semi-ring has to include two special values called a 0 and a 1. The 0 is an additive identity, meaning you can add it to anything without changing the thing. And a multiplicative annihilator, which means if you multiply anything by the 0, you get 0. And then it also has to have a multiplicative identity called 1. And there are two operations we'll call them abstractly plus and times. Plus has to be associative and commutative, and times has to be associative. And then there's this distributivity property. The times has to distribute over the plus. This is what we've exploited to get our efficient algorithms so far. So I'm not going to give you mathematical definitions of these. It's easy to pause the video and look them up if you don't remember. But here are the two semi-rings we've actually been working with in the lecture so far. The real semi-ring is the semi-ring that interprets each of these abstract things in the most literal way possible. So 0 is 0, 1 is 1, plus is plus, and times is times. The Viterbi semi-ring, which we used in the Viterbi algorithm, only makes one change. It changes the plus to a max. So essentially, you can show that all the properties on the last slide still hold when we do that for this new Viterbi semi-ring. Interestingly, all of the only values we're really concerned with are the non-negative reals. These algorithms don't ever encounter negative values. And so everything here makes sense in that setting under these assumptions. But here are some other semi-rings that you can consider. One is the Boolean semi-ring, where the values are only 0 and 1, and we replace plus with or and times with and you can show all the properties hold. And this is useful if you simply want to know whether the HMM can produce a string at all. Is there a way to generate the string with non-zero probability? You can also change things slightly to get a semi-ring that lets you count how many valid labelings there are. If some of the transition or emission probabilities are 0, then the actual number of labelings might be smaller than size of lambda to the n. And I think we saw an example of this earlier in the lecture. In practice, on modern computers, we often implement these algorithms not using real value probabilities, but rather using log probabilities. And so you can actually think about this change as just a shift in the semi-ring, where the values are now negative numbers or non-positive numbers corresponding to the log probabilities. And the operations change slightly. The times becomes a plus, and the plus becomes an operator called log plus. And people have introduced all kinds of cool semi-rings for things like finding the k-best label sequences, generalizing beyond Viterbi, and switching the sign where instead of maximizing a score, we're trying to minimize some kind of cost. And if you analyze Levenshtein edit distance algorithms and Dijkstra's algorithms as dynamic programming algorithms with recurrence equations, the way we've shown Viterbi and forward and backward, then it's helpful to think about minimizing rather than maximizing. So the plus becomes a min, and you interpret your values as costs. Okay, so stepping back. That's a long kind of tangent off of this interesting analogy between the Viterbi algorithm for finding the most probable state sequence, that was our first problem, and the forward algorithm for finding the total probability of the word sequence, that was our second problem. Now I want to ask a more fine-grained problem. So suppose that I have my sequence of words, and what I'm interested in is asking for any particular word, or maybe for all words, what is the distribution over states under the model? So leaving all the other words out, if I look at the word at a particular position, what should I believe about the states that might have generated it? Okay, so this is a question where we're not asking about the whole sequence of states. We're asking about one state at a time. And we did do local reasoning because we had to do local reasoning in order to reason about the whole sequence. So either find the best path, bold S, that goes from 1 to n, or finding the total probability averaging over all possible paths, paths probabilities. So in order to think about the more fine-grained question, I like to use a graphical representation that lays out all the random variables for us and kind of colors them according to what we want to do with them or how we think about them. So to start out, here's the graphical model representation for what an HMM believes or assumes about how the data were generated. So this is just kind of a graphical view of what we said before. Every node here is a random variable that's going to take some value. And the incoming edges to a random variable tell you what other random variables it conditions on directly. So we sometimes call those its parents. And you'll notice in the HMM, in the first order HMM, every node only has one parent. And that tells you what we conditioned on when we generated the value for that node's random variable. So W1 was drawn according to the emission distribution for state 1. State 2 was generated according to the transition distribution for state 1, and so on. So we have this nice chain structure where each state depends on its predecessor and each word depends on its corresponding state. Hiding inside this visualization are the parameters of our model. We'll come back to this more when we talk about learning later, but it's sort of implied that on each arrow, there has to be some parametric form for the probability distribution over the child random variable given its parents. And so that's where the gammas and the etas, the transition and emission probabilities, are hiding. They're associated with those particular edges. Okay, so I like to augment the random variable graphical model notation with colors when I think about different kinds of questions that I might ask using the graphical model, using, in our case, the HMM. So I'm going to use gray to denote variables that are observed, so that corresponds in problem 1, finding the best path, to the observed information, observed evidence. In this case, it's all the words. And I've colored red the state sequence because what I want to do is collectively assign values to the states, maximizing the probability of the whole configuration. So the goal is to calculate the best value of the probability for any assignment of red variables respecting the gray random variables, which again we call the evidence. In problem 2, the graphical model looks very similar, but we use a different color because what we're actually interested in is not the probabilities of these individual random variables at their maximal values, but rather we want to sum them out. We want to sum over them. We're not interested in what values they take. We want to consider all of them and then kind of forget about them. So the sequence of words is still observed. They're still gray, and we use blue to denote the random variables we want to marginalize or sum over. So the goal is to calculate the best value of probability for any assignment to the red random variables, but there aren't any. So there's really only one value here to consider. That's why we're not maximizing anymore. We're just summing, respecting the gray evidence, and summing over all possible assignments to blue random variables. So no red random variables here, and in problem 1, there were no blue random variables. We're only summing. In problem 1, we were only maximizing. So problem 3 is interesting because now we can sort of use the same abstract goal formulation, calculate the best value of P for any assignment to the red random variables, respecting the gray random variables, and summing over all possible assignments to the blue ones. But now we're interested in picking one state, let's say state 3, and finding its most probable assignment, or maybe the distribution over its values, after summing over all the possible assignments for all the blue variables, all the other states. So we're thinking about just a single word state at a time here. By the way, I'm using this notation specifically for the hidden Markov model, but you can easily imagine adding extra edges or extra nodes and really expanding this kind of model to make very different assumptions about our data. And when you go that route, what you're essentially doing is you're exploring the realm of probabilistic graphical models, which are an extremely useful framework in machine learning and NLP, and a very useful way to analyze data that involve many dimensions. Hidden Markov models are really just one kind of graphical model, and you may have heard of others like Bayesian networks, Markov networks, and factor graphs. This is a really fascinating research area that is, I think, quite complementary to the kind of learning that we see emphasized today using neural networks, because neural networks are really focused on the form of the probability distribution when they define probability distributions, whereas these network models are really focused more on the independence assumptions that you make about different aspects of your data. I think the two fit together nicely, and that's a really fruitful area for continued research and an active area of research. Okay, back to our problem. Remember, we want to find the distribution over values for state I, conditioned on the words, and summing out over the values for all the other possible states. So on this slide, I've written out a formula that notes that in order to do this, to calculate this quantity, what I need to do is I need to sum over all the possible state values for 1 through I minus 1, and I plus 1 through n. And so I've broken the summation, the first line here breaks the summation into those two parts, and notices that the two subsequences to the left and the right are conditionally independent given the value at state I. So I can use my distributive property to break the, well, first I can use my independence assumption to break that larger probabilistic quantity into these two factors, and then I can notice that the first one only depends, the first of the factors only depends on the prefix, and the second one only depends on the suffix. So I can separate the two out and calculate them completely separately. And so I have the sum over the prefix, and then the product of the prefix probability times the sum over the suffix. And when you squint your eyes and match this back to what you've already learned, you notice that the first quantity is a forward probability and the second one is a backward probability. So if I had done all of the forward and backward algorithms sets of pre-calculations, I could simply look up these two values, the forward probability up to position I for state, for this particular state, and the backward probability up to position I for this particular state, and multiply them together, and I would get the joint probability of the words together with that particular state. Okay, sometimes I like to sort of use a gray box to suggest that I'm summing things up, and the quantity associated with each of those two sums is a forward or a backward probability. So if I run the forward and backward algorithms to produce all the forward and backward probabilities, we can, or even just stop at position I. I don't even have to run the algorithms all the way to the end if I only care about one position. And then I now can multiply together the forward and backward probabilities for each state to get the joint probability of the words together with that state. If I renormalize this, then I get the probability of the state given the words. And this is just following from the definition of conditional probability. And this quantity is sometimes called a posterior. It's the posterior probability, or the after I've observed the evidence of the words, probability of position I taking state sigma. And that denominator, I want you to notice, is actually the same thing that either the forward or backward probability gave us. This gives us kind of another way. There's another way to calculate the total probability of the sequence, if you work through this carefully, is to pick a position I and run the forward algorithm and the backward algorithm both up to position I, and then take an inner product of those vectors. Kind of fascinating how many different ways there are to calculate the probability of the words given the model. Okay, so now you know how to calculate the probability distribution over states for each word, reusing the same algorithm we used for problem 2. We're now going to turn to something else you can do with these quantities that's quite interesting. Suppose that I've done the forward and backward algorithms, and that took me order n times lambda squared time. And so now I could take what I learned for the last problem and apply it to every word position. I could essentially choose for every word the state label that maximizes, that has the highest probability according to these posterior distributions. So this is a local labeler that considers all the possible labels for this word at position I, and just picks the one that has the highest forward times backward probability. And this would be a very different way to label the words in the sequence, or to make a choice about each of the words. It's sometimes called posterior decoding, in contrast with what we did in Viterbi decoding. And this is really, it's really interesting, I think, to think about these two approaches and what implications they have, because in general, they won't do the same thing. What's going on with posterior decoding is we're exploiting the model's full distribution over all sequences to choose each word's label. So for each label, we're choosing for each word, we're choosing the label that has the highest posterior probability, taking into account all possible labelings of all the other words. When we compare this with Viterbi decoding, or actually its technical name should be maximum a posteriori decoding because it's choosing the most probable state sequence collectively overall. All the words are getting jointly labeled to maximize the total probability of that one path through the HMM. Sometimes we slip and call it Viterbi decoding because that's the algorithm that we use to accomplish it. Okay, so these two things, they look very different. I'm going to give you kind of a way to think about them. I'm not going to tell you which one to use. There's not really an easy answer to which one you should use in a particular situation. It's important to note they will not in general give you the same label sequence. People have seen in some cases one works better, sometimes the other. It probably depends a lot on your model and your data and your problem. Posterior decoding can actually do some weird things, like it might give you a label sequence that itself does not have positive probability because it sort of uses, for example, a lot of evidence on the left to label word at position I and a lot of evidence on the right to label a word at position I+1, but those two labels can't transition to each other because they have zero probability in the HMM. But you might still make a choice like that. And whether that's bad is sort of a matter of, it depends on your task, your application, your situation. So I'm certainly not going to tell you which one to use, but instead I think it's more useful to try to unify them and understand why you might choose one or the other and why we might expect one to work better than another in a given situation. So in order to do this, we have to introduce a new notion of something we're going to call cost. So imagine that once we've constructed our HMM, we're going to play a game. And here's how the game will work. The HMM will be given a new word sequence, W, and it's going to be used to label the sequence. Okay, I'm not going to say which algorithm to use. I'm just going to say the goal is to label the sequence. And then after that's done, the hypothesized guessed label sequence S is going to be compared to the true correct one, S star. And this is kind of like what happens when we test our model, right? We see what the model says, and then we ask, how does this compare with the gold standard? But what's a little different is that unlike in an experiment to analyze a model, what we're going to have to do is pay a fine or a cost depending on how badly we do. And our goal is, of course, to minimize the cost, right? We'd ideally like to get everything right and pay no fine. So without having seen any word sequences or knowing what particular instances we're going to need to work with, we need a strategy. And my claim is that our strategy for labeling given the HMM is going to depend on how the cost is going to be defined at the end. So here's the first version of cost. Suppose that if you get the sequence wrong at all, even one word, at all wrong, if you don't get it 100% right, you pay €1. Otherwise, you pay nothing. This is called all or nothing. Okay, this cost is called all or nothing because you either get it all right and you pay nothing, or you get it even a little bit wrong and you pay a full €1. And so here's my claim. I'm not going to offer a proof, but there is one. If you trust the distribution given by the HMM over words and state sequences, then you should use Viterbi decoding. You should choose the state sequence that is most probable under the model, because it puts well, you believe the distribution is correct, and what you care about is maximizing the chance that you don't pay €1, which means you should bet on the full sequence that that the model thinks is most likely. But there's a situation that's a little different where you might want to do something else. So suppose that instead of paying €1 if you get anything wrong, you pay a smaller amount, let's say €0.1 of €1, for every word that you label incorrectly. So this is more fine-grained, it's more forgiving. A small number of mistakes is better than a large number of mistakes, unlike the previous model where any mistakes are equally bad. And it suggests that we should focus on reasoning about each word without worrying so much about the coherence of the sequence. You should place a bet locally for each word and choose its most probable label, which, if you trust your distribution, which you should, otherwise what's the point in building a distribution, then you should use posterior decoding, and you should make local decisions, reasoning about all possible paths for each word. So both of these can be unified using the concept of minimum Bayes risk, which says, assume we have a good estimated distribution over words and state sequences. The general decoding rule that you should use is to pick the sequence that minimizes the expected cost of your choice. Okay, so pick the S prime who, under your distribution over what the states are, your beliefs about what the states are, you should pick the sequence that on average under that distribution will have the lowest cost. Pick the S that's least offensive in an expectation, but you can't talk about how offensive each label sequence is without knowing how much cost you would pay if you made that choice. So with the all or nothing cost, you get map or Viterbi decoding under this decoding rule, and with Hamming cost, you get posterior decoding. There are actually more things to be said about this. So we can generalize even more and imagine that we have a generic cost function that decomposes into a sum of local costs. Maybe we have a different cost function associated with every word in the sequence. We can call it cost I at position I, and we have a little matrix telling us for every possible true label at position I, what's the cost we would pay for every guess. And this matrix might be different at every position in the sequence. If the Hamming cost is an example of this, where we've essentially said that you pay 1 or some fixed cost at every position where S prime doesn't match S, but there are more, and you could actually define any cost function you wanted, and as long as it's local, you can exploit the forward and backward formulas to find the minimum cost choice at each position, minimum expected cost choice or minimum Bayes risk cost choice at each position. Turning this around a little bit, it leads us to kind of an interesting idea I like to think about, where you get to manipulate the cost function. So here's a concrete example that's kind of interesting. Suppose we're using a hidden markup model to do named entity recognition, and our tags are B, I, and O. Let's just not worry about whether we're dealing with the difference between person, place, organization, and so on. We just have, where are the named entities? Let's find the spans that correspond to named entities. When you solve a problem like this, you might be more interested in precision than recall, meaning I only want the things I find to be correct. I don't mind if I miss some, as long as the ones I get, I choose to be named entities mentions actually are very likely to be named entity mentions. If I care about precision, then I might choose a very different cost function that penalizes some kinds of errors more than others. And conversely, if I care more about recall, I want to find all the named entity mentions. Even if I also pull in some noise, then I care about recall, then I might choose a different cost function. So to make that concrete, suppose that we have a different cost for a recall error versus a precision error versus a boundary error, where I choose the wrong beginning or ending point for a particular named entity. Here what I've done is I've written out a confusion matrix of all the BIO sequence pairs or bigrams of labels that are possible. There are 8 possible ones. The only one that's missing here is OI, which is not allowed. You always have to have a B before an I. And what I've done is I've manually categorized each of the possible errors here as being a precision error or a recall error or a merge error or a split error. You can pause the video and check my work. I'm not going to walk through these. It would be a bit tedious. There's also some that I didn't label because I didn't really know how to think about them. But the idea is you can define a cost for each of these based on this equivalence class, or really anything you want, and assign different errors to each cost. But now this leads us to a slightly different kind of posterior, because in order to calculate the expected cost over these pairs, I have to calculate posterior probabilities of pairs of state labels. And because these things are adjacent and the math kind of works out nicely, I can still do this using the forward and backward probabilities. So basically, instead of looking at the posterior probability of one state at one word position, I'm looking at a pair at two adjacent word positions. And if I work out the formula, which I've done here at the bottom of the slide, where I'm interested in the joint probability of the two state sequences with the words, the two states adjacent to each other with the words. Again, I can decompose this into a prefix and a suffix probability. It's just they are separated by two instead of one state in the middle. And then I take into account the transition between those two states in the middle and the emission, the one missing emission of the second word given the second state that isn't folded into either the prefix or suffix marginals. What I can see if I squint my eyes and remember the definitions is that this is a product of a forward probability, a backward probability, and a single emission and transition in the middle. So I can essentially use all the same calculations to get the two-state posteriors, and I can use this to decode it. Here's a graphical representation of that. There are now two adjacent states which are red. I use the forward and backward probabilities, also account for the transition and emission that are not summed over in those two quantities, and I can score every possible state sequence, two-state sequence at this position according to its posterior probability. So there's a little bit of a weirdness about this kind of labeling approach where we use two-state posterior decoding. And here's the issue. It's possible to label every adjacent pair of words, but doing this doesn't guarantee that we're going to have consistent labels when consider position I. It's going to show up in two pairs, one to its left and one to its right, and I might get different answers for this word's label from the left and from the right. So here's a total solution to pairwise minimum Bayes risk that puts together all the pieces from what we've learned. Here's how it works. First, you run forward and backward, and you get all the prefix and suffix marginal probabilities, the forward and backward probabilities. And then we use the posteriors to score all the possible label pairs for all the adjacent words with their expected cost. And so now what we want to do is find the least cost total sequence that's internally consistent, that minimizes the sum of these expected costs. So you're going to use something very similar to Viterbi. You're going to think about the expected costs you just calculated as being kind of like log probabilities, except you want to minimize instead of maximize. You're going to use the min cost semi-ring, and you're going to score each of the label pair candidates at each position by the local cost times, for that choice, times the posterior probability. So we call this the local risk. And so you've used dynamic programming twice here. Once to do all the pre-calculation that lets you score every possible two-state sequence at every position, and then you use dynamic programming again now to optimize, finding the min cost path to find one best scoring labeling that minimizes the sum of those expected costs. Okay, to sort of test your understanding and synthesis of all of this, I'm going to ask a question. Can you think of a cost function that we could use that would, such that the minimum Bayes risk decoding with that cost function would not be doable in polynomial time? So I've shown you several different instances of minimum Bayes risk, exploiting what we learned about Viterbi and forward and backward, and then I introduced this two-state one. Can you think of another cost function that wouldn't be easy, that wouldn't let me use all these dynamic programming tricks? I'll pause for a second. So here's the answer, or an answer. Suppose I have a constraint that every word in the sequence must get a different label. Or equivalently, you can use each label at most one time. Another instance would be you have to use each label exactly once. Which I think this one's a little bit clearer why this one doesn't decompose nicely. It's essentially Hamiltonian path. You may remember that solving such problems in polynomial time is believed by most not to be possible. So essentially, what's wrong with both of these, or what makes both of these kinds of cost functions computationally challenging, is that they're essentially saying that the label choices at every position kind of depend on the label choices. No, not kind of, really depend on the label choices at every other position. The reason we can use dynamic programming for all of the cost functions we've talked about here is that the costs decompose into things that can be calculated very locally. Okay, that's a good place to stop this segment.
Okay. In the interest of time, it might be good to just kind of proceed to the next video, if that's what you guys think, and I can just keep taking questions as they come. I know. One thing I've always thought about this lecture is it tends to speed up as we go along and like get more dense. So I know this is kind of like sipping from a fire hose for some people. There's a lot going on, but the last part is the exciting part where we finally talk about learning. So maybe we should go there.
Okay.
I'll keep watching for questions though.
Okay, let's move on.
Okay, welcome back for the fifth and last video in the sequence models lecture. Just a kind of a comment. It may seem very strange to you that we've spent 4 out of the 5 chunks of this lecture and barely talked about learning at all. This is a machine learning summer school, so where's the learning? And I think it's helpful to point out before we dive into learning, which I promise we will, that you know, of course, there's always learning when you're building an AI system. Data is really, really important, and it's kind of impossible to imagine that we could have made the progress that we've made in the field without doing learning. But the models that we learn aren't just there as products of learning. They can also do other things for us. And I think the hidden markup model is a really nice illustration of that. It's a model that encodes some assumptions, helps us think through what we believe about our data, and it lets us answer lots of different questions. So in the last section, we talked about a whole bunch of different questions you could answer if you had embraced the HMM and wanted to use it as a lens to look at your data. Anyway, there is learning, and we're going to talk about learning now. And so this is the last piece of the puzzle, and there's quite a lot we could say about learning algorithms for hidden markup models. And I'm going to give you the classical foundations, and at the end, I'll point you in a bunch of exciting newer directions that are probably a little bit more pertinent to what you're doing today. But when you go to discover them, you'll have a very strong foundation, I hope. Okay, so the typical place we start when we talk about learning hidden markup models is that we have some data, and we've already decided how many states our hidden markup model has. And we may have some constraints on the states, like, for example, if we're doing named entity recognition or some kind of chunking task, we may be using the BIO formulation I talked about a while back, which has a constraint that you can never have an I directly following an O. It doesn't make sense in the label space. The interpretation of the labels fails. So you may have constraints like that, but for now we're not going to worry about that. We're just going to assume that we've chosen HMM. We've decided how many states we have. And there are sort of two, although there are many settings you might find yourself in, there are sort of two paradigms that are worth discussing in some detail. And I'll call them the supervised and unsupervised cases. In the supervised case, you get example pairs of words and sequences. And in the unsupervised case, you only get the words. And so we'll talk about supervised first, because that one's easier and faster. Okay, so here we are again with the HMM. Just to remind you, the building blocks of the HMM are multinomial probability distributions, the collection of distributions gamma over the next state given a particular current state. So there's one of these gamma distributions for every current state. And then the distributions eta over words given the current state. And we have, again, one of those for every possible state in our model. If we turn to statistics and say we have probability distributions, how should we pick their parameters? How should we assign probabilities to the events? of going to the next state or emitting a particular word. Statistics says your starting point is called the maximum likelihood principle. You're going to choose parameters that make the data you have as likely as possible. And that's all that this math is trying to say. Pick parameters to make the data you observe as likely as possible. I'm not going to give a formal treatment of this point, but it's what you're exploiting when you do supervised HMM learning. The fact that the distributions for each state and each transmission can be estimated separately, both from each other and from those of all the other states, follows from the fact that your data is fully observed. The best way to understand this is, where's my picture, is to look at the graphical models view of learning. So here I've augmented our graphical model with two nodes, one for the gamma distributions at the top and one for the eta distributions at the bottom. And what I want, and then notice that I've used the colors like I did before. So we want to choose the gamma and the eta values. So we're kind of like pretending the parameters are random variables, which may feel a little bit weird, but it's one of the cool things about the graphical model framework is that you can actually pack quite a lot into these representations. So, okay, so notice that the gamma and the eta are red, meaning we want to choose the values, and all the words and all the states in the sequence are gray because we observe them. And the main property I want you to see is that there's this big wall of gray between the red nodes. And if I separated out every gamma and eta distribution separately and made more bubbles for each of these guys, there'd be a bunch more red bubbles, but none of them would be connected to each other, and they'd all be separated by these gray nodes. And so that separation property, if you study graphical models in greater detail, you'll learn that allows you to reason separately about the different parameters in the HMM. And so that means that you don't have to, there's no interdependence in choosing the parameters. You can gather some statistics and then solve each little problem for each little distribution separately. And so here's the formula, and it's almost silly, I think, to put it on the slide and dressed up in so much math, because this is something that people tend to feel very intuitively, that when they want to estimate the probability distribution, a multinomial probability distribution, what they're going to do is they're going to look at relative frequencies. We did this earlier, you remember, in the Markov model case, and I didn't give any formal treatment there. I'm tempted to give you the math and derive why this is the maximum likelihood estimate, why relative frequencies are the solution when you want to do maximum likelihood estimation with a model like this. I'm just going to show you the math. You're counting frequencies of state transitions or state emissions, and then dividing by the total number of times you visited a state. And those relative frequencies give you the weights for the different sides of your two kinds of dice. In order to get to this solution, the way you derive it is you write down the log likelihood formula for your model. You say, I want to maximize this. You use a Lagrangian multiplier to force the probabilities to sum to 1. You take derivatives and set to 0, and the rest is basically algebra. I don't think it's important that you know how to do this from scratch. I think it is important that you understand that there is a theoretical reason why we use relative frequency estimation. Okay. So maximum likelihood estimation is a widely discussed and studied technique. And distilling many years of study and research, I'm gonna put forward the sort of rule of thumb is that it works pretty well when you have a lot of data. But you never have as much data as you would like, particularly when you are doing NLP in the supervised paradigm. So we just never have enough labeled sequences with their states. The data sets that people have taken the time to build are great, but they are always too small. Language is very complicated, and there's a lot of tail-end phenomena we're probably never going to see with our finite data set. Okay, so one way to go about trying to inject some background knowledge into our HMM learner, or really any learner, is to construct a prior. And this is, there are many reasons to talk about priors, and this is not going to be a lengthy lecture in why you might consider being Bayesian. The sort of practical thing to say about priors is that a good prior usually helps you avoid overfitting to the training data and helps you generalize better. There's a lot of philosophical claims we could go into about priors, but I'm basically just giving you the practical argument. If you're doing something like MLE with something like an HMM, a prior is probably going to help you do a little better. And so that leads us to something called maximum a posteriori learning, or MAP learning, where instead of maximizing just the likelihood of the evidence given the parameters, we multiply in the prior probability of the parameters. So when I say the prior in this part of the lecture, I'm referring to a distribution that we embrace before we start learning over the parameters of the model, the gammas and the etas. Okay, so multiplying these things together gives us a joint probability. The whole expression here I can point at the bottom of my slide is the joint probability of the parameters and the evidence, rather than the conditional probability of the evidence given the parameters. Okay, so how do you get prior probabilities over multinomial distributions, which HMMs are built out of? There's a very easy to work with and simple solution that's a good starting point called the Dirichlet distribution. And it's a family of distributions over multinomials. So when you sample from a Dirichlet, you get a die with weights on the different sides. So you can think of a Dirichlet as like a random process for making dice. The simplest version is something we call a symmetric non-sparse Dirichlet. And I'm not gonna walk you through the math because it's a little intimidating, but I am gonna walk you through how you can use it in practice. And you can read up more if you're interested in the theory behind it and the generalization. So for transitions, you're going to pick a value alpha t greater than 1. And for emissions, you're going to pick a value alpha e greater than 1. And basically, the bigger the values you pick, the more strongly you're encouraging your probability distributions in your model to move toward uniform, or to be a little bit more flat rather than peaky. And so what you do, but in practice, before you take your frequencies and normalize them, you're going to add something to the counts. So you're going to add alpha t minus 1 to the transition counts, so a positive value, and alpha e minus 1 to the emission counts, also a positive value. There's a little bit of history around why we subtract 1 first, and this is really just so that the notation in my slides matches what you'll see in a textbook if you go read up on Dirichlet's, which I hope you'll do. But really what this means in practice is we're adding some fixed positive value to every transition or emission count. We're also adding the sum of all of these to the denominator, so things will sum to 1, and we renormalize as usual. This is exactly the same as the additive smoothing techniques we mentioned in language modeling, and in fact, Dirichlet's can be used in language modeling as well. It's essentially adding a pseudo count and pretending that before you looked at your data, you already saw every transition and every emission happen some number of times. A very common choice is to set these alphas equal to 2, so you're adding 1 to every count. In the graphical models view, you can pack this in as well. You can think about this as a way of saying that your gamma and eta distributions were drawn from their respective priors. And so the alpha bubbles there are denoting those priors, and they are gray because we fixed them in advance. We've just asserted that we know their values. We're not trying to update or estimate them. They're just fixed values. Okay, so now let's transition to the unsupervised learning case, which is actually has arguably a longer history, and there's quite a lot more to say about this situation. So going back pretty far, back to the 1960s, the name hidden Markov models was evoking a notion that we were going to use these models in the unsupervised case. That the word hidden means we do not see the states that the tokens, the words are generated from. So my discussion around supervised HMMs and their application in NLP with fully labeled data is a little bit bizarre relative to the original formulation. And that's why some additional clarification may be needed if you go talk to friends who don't know NLP, who are trained in engineering or in pure machine learning. You may need to say, we're doing HMMs, but we're assuming that the states have been observed in at least some of our data. Here, we're going to switch and say, no, they were not observed. So we're going back to the very classical setting. And this has a really, I think, important place in the history of machine learning, because the HMM was really the earliest instance, at least to my knowledge, of a case where we were trying to learn parameters of a model and the data were incomplete. So we only get words. Could we possibly learn the distribution of the states we pass through if we never observe them, if we only see the words? And so here's the cool kind of aha moment in this lecture. I've actually given you all the things that you need to do this using the standard approach. And there are two components. One is maximum likelihood estimation from statistics, which we just discussed. And in practice, that's a fancy way of saying count up events and normalize the counts, and then you can estimate the probabilities. And then the other side of it is the computational side, where we're going to need to do some inference and calculate posterior probabilities that different events happened, or that different states were visited at different times in the data. And we talked about that at great length in the last chunk when we talked about the forward and backward algorithms and all the interesting things you can do with them. And so, while it may have seemed strange that I was going on and on about all these different things you could do with the forward and backward probabilities, this is where it pays off. We're going to use all of these techniques to put together an algorithm for unsupervised learning. So I think it's helpful to have kind of a high-level overview, and the visualization, I think, is really, really useful here. So again, here's our HMM. I've added in the parameters, the gammas and the etas, and they're colored red because, just like in the supervised case, our interest was in choosing values or inferring values for the parameters for gamma and eta. The only difference from the most recent case with supervised learning is that now the state random variables are all blue because we don't know their values. And we're actually, when we're learning, we're not actually that interested. What we'd like to do is say, let's make the words as likely as possible, whatever their states were, and take all possible state sequences into account while we're learning, because we don't want to make a commitment. So this is a view of the unsupervised learning problem as a graphical model for an HMM. So key here is that you have red and you have blue. Easy test, right? I see red, I see blue, and that means we're doing mixed inference. We want to sum out some random variables, the blue ones, and we want to pick values for the others, the red ones. And this, in general, is a very hard thing to do. In general, this is a hard problem, and in general, finding the maximum likelihood estimate when you have latent variables, hidden variables, is an NP hard problem. And there's an optimization way to talk about this as well, which if you started studying deep learning will be familiar. Solving this problem involves optimizing a function that is not convex in the parameters. So unlike the supervised case where there was a closed form solution, which provably was the global optimum of a convex function, we're in a totally different territory now. Okay, so the solution that I'm going to tell you about is called the EM algorithm. And EM stands for expectation maximization. It's also a mnemonic for the two parts of the algorithm. And the two parts of the algorithm decompose that graphical model that we just saw in a very elegant way. So EM are the two steps, the E step and the M step. The E step is depicted on the left. In the E step, we don't worry about the parameters. We assume that the current values that we've most recently chosen for them are fixed and correct. And we do inference, soft inference, over the missing parts, which are the states. So we're going to, on the E step, infer the posterior distribution over each of the states that we might have passed through at every time step corresponding to every word. But we don't worry about the parameters, they're fixed. The M step is the inverse of that. We're going to leave the missing data alone. We're going to assume that the most recently estimated values for the missing data, which are soft posteriors, a distribution for every state, we're going to assume those are correct, that we have fractional observations of having passed through every state at every time step. And we're going to focus instead on updating our parameters to maximize the likelihood of the total data, including the missing data we've filled in. So the problem on the left is an inference problem, soft problem, summing problem. The problem on the right looks almost exactly like the supervised learning case we covered just a few minutes ago. And so the EM algorithm alternates between the two. It updates the posteriors, and then it updates the parameters. Posteriors, parameters, E step, M step, back and forth. So here's the procedure. You have to start out somewhere. And usually we say we start off with an initial estimate of the parameters of the HMM. Usually we pick it to be random and close to uniform, but there are different ways of doing it. For your particular problem, you might start with a small amount of labeled data to pick the parameters. You might have some prior knowledge about how to pick the parameters and do it manually. There's a lot of things you can do, but somehow you get an initial estimate. And then you repeat. E step, calculate the probability of every possible transition and every possible emission at every position in your data. And we'll use, just to foreshadow, we'll use a forward-backward algorithm to do that efficiently. And then on the M step, you re-estimate the parameters to maximize the likelihood of the complete data that you filled in now on the E step. I'm going to talk about the E step first, then the M step. So to put it in mathematical terms, we need the probability of the state sequence for every possible state sequence. And from that, we want to count every possible state sequence proportional to its probability. Another way to say it, that's sort of the more easy to grab on version of what's happening on the E step, but what we practically do doesn't actually ever enumerate all the possible state sequences. The way we think about this in practice is we're calculating the probability over possible values of SI for every position I, and count every emission of word I from SI proportional to its probability. And similar for the transitions. We calculate the posterior probability of every state pair, consecutive state pair, at every position I, and count each transition from SI to SI plus 1 proportional to its probability. This is much more manageable because there's only a finite set of things, a polynomial set of things that we have to enumerate, states and state pairs at each position, rather than full sequences, which, as we remember, explode exponentially in the length of the sequence. So we're given the words and the current parameters. We run the forward and backward algorithms, and we obtain these posteriors: probability of a state at a given position, probability of a state pair at a given position. And these posteriors will sum to 1 at each position. You can think of them as like taking a count, a single event happened, there's one thing, but we're dividing it up fractionally or softly across all the possible events that might have taken place. And then once we have, so here's the math showing you how you can calculate these soft frequencies by using the forward and backward quantities. This is really just a review of what you saw earlier in the lecture, and I would not have expected, given the speed at which we're going, that you would be able to reconstruct these from memory. But you should have this intuition that that summing across all the positions in the data, the posterior quantities that we calculated earlier, gives you these soft frequencies. So notice each of these expressions has a sum over some or all of the positions in the data. So these soft frequencies are just like the frequencies we saw before, except that they're averaging under the probability distribution over all the possible ways that the state sequence could have proceeded given our data. Okay, so back to the high level. That was the E step. Let's talk about the M step. The M step is analogous to the supervised case where we had observed hard evidence for events at every time step. So at the top of the slide, you see the hard counts. You renormalize the frequencies of state transitions and state word emissions. Here, you do exactly the same thing. The only difference is that now your frequencies are wearing hats because they are, in my notation, they are soft, and therefore they have hats on. They are soft expected counts rather than hard actual counts. But the formulas are the same, and the computational cost of this renormalization procedure is basically linear in the number of parameters. It's quite cheap and fast. In practice, when you run the EM algorithm for HMMs, most of the work happens in the E step. It is the most error-prone thing to implement because those equations are kind of complicated. The forward and the backward steps are easy to get a little bit wrong. Managing the log math often trips some people up. It's kind of a complicated thing to get right. The M step is usually pretty close to trivial because it looks so similar to just normalizing vectors. Okay, so I've given you this algorithm. What can I promise you if you use it? I cannot actually promise you very much. Here's the good news. Every iteration that you run of the EM algorithm will improve the likelihood of your data. So you are, in fact, climbing up the likelihood surface, and you'll get a model that's a better fit to your training data every round. And eventually, you'll converge to a local optimum or a saddle point. In practice, we don't usually worry about saddle points, just like in deep learning. But the key thing you need to know is that if you run this algorithm multiple times from different starting points, you will probably get different solutions. Sometimes those different solutions will be similar up to a rotation of the states. So if you kind of imagine switching state number 14 and state number 17, you effectively have the same likelihood, and you'll have more or less the same model up to the labeling of the states. So there's an inherent symmetry here where you could swap any of the states with each other and still expect the same likelihood because the states don't have any inherent meaning. They're really just kind of like clusters, really. But there may be other reasons for many local optima, and there are sometimes people find degenerate solutions where the HMM behaves really badly for various reasons having to do with your data. So initialization really, really matters, and I put this picture of a mountain near where I live to remind you of this. The image you should have in your head whenever you do non-convex optimization is that your friends have airlifted you onto a random point on the mountain, and you're blindfolded, and really all you can do when you carry out these local greedy algorithms is use the soles of your feet to feel which way is up and take a small step in that direction. And there's no guarantee when you do that you'll land, that you'll ultimately get to the very top of the mountain. A lot of things could go wrong. In our metaphor, you might end up on a small local hill that doesn't have any direct upward path to the top of the mountain. Only taking local upward steps doesn't guarantee you'll get to the top. That said, I want to point out, at least you know what you're optimizing, and with today's hardware, it's not crazy when you want to do something like this to start, 10 or 100 different models at different points, and ultimately choose the one that gets to the greatest global optimum. The greatest local optimum. Again, no guarantees. But it's worth thinking, I think, still about practical ways to get around this challenge. Okay, so there are some variants that are worth mentioning. The fractional count thing, I think some people find it very intuitive. Other people find it kind of weird and overwrought, and they think the probability metaphor maybe isn't so important. So it's worth mentioning something called hard EM, which is extremely similar, but it doesn't have quite as much of the probability stuff. So the idea is that your E step, instead of doing fractional counting, it just chooses the current model's favorite state sequence for your words by running the Viterbi algorithm. And then on the M step, we just treat that Viterbi path as a true observation and use hard counts. And so this is sometimes called self-learning. You use the model to label the data, and then you use the newly labeled data to retrain the model. Some people find this very intuitive and attractive. It has worked sometimes better, sometimes worse than soft EM. Some people find this very, very troubling, like, how do I know I'm not just spinning around in a circle? You actually don't know that with any of these models. It's important to remember that there's never any guarantee that running an unsupervised learner is going to recover a view of the data that corresponds with your own personal interpretation, what you would do as a human.
So anyway, hard EM is justified by saying that you're doing coordinate ascent on a maximization problem like this, where you're maximizing the probability of the words in the states with respect to both the states and the parameters at the same time. And so you're doing block coordinate ascent, where on the E step you update the states, and on the M step you update the parameters, the gammas and the etas. Some people like it better. There's no deep theoretical reason why you should like one or the other. They're adopting different assumptions about what you want to do. People have found for the same model that the Viterbi version is usually faster to converge, but again, it's optimizing a different surface, so you should not expect it to get you to the same solution. And again, the only difference is that on the E step, you use Viterbi to choose the label sequence rather than forward-backward to score all possible sub-events within the label sequence. There were some arguments at one time that maybe it's more brittle. It's really not clear. There's not a lot of theory on this. Okay, stepping back a little bit, I presented to you the EM algorithm as applied to hidden Markov models. But in fact, EM is an incredibly general technique. It was originally introduced in the 60s for HMMs by Baum and Welch, and it was for a long time called Baum-Welch training in that case, or forward-backward training for the obvious reason, uses the forward-backward algorithm. But anytime you have a generative model of your data, you can apply EM. And very often people that I've taught in this lecture or in other NLP classes have seen the EM algorithm applied to mixtures of Gaussians or other kinds of clustering models. And in fact, if you know the k-means clustering algorithm, you can interpret it as a kind of hard expectation maximization. So, the connections among methods and algorithms in machine learning are often surprising. And I tend to think that different ideas in machine learning that often lead us to very similar approaches. And I think that's something worth noting. And it also makes it much easier to learn the field, I think. I want to say a little bit about the connection of hidden Markov models to some other mathematical tools that come up in NLP and machine learning from time to time. This is an area I've always found really fascinating. If you have ever taken a class in formal language theory or theory of computation, you may have encountered finite state automata or finite state machines. I'm going to give you the loose, not very technically deep or notation heavy version of this and draw some connections because you may have already had this intuition. An HMM is a finite set of discrete states, and it has a set of allowed transitions between the states. And the idea is that you can walk non-deterministically among the different states according to what transitions are allowed. And when you go to a state, you generate a symbol. Or alternately, in a slightly different notational variant, when you walk along a particular transition between two states, you have a choice. You have a choice of symbols you can generate. Finite state automata sound a lot like HMMs, and in fact, there is a connection. If you change the non-determinism part of a finite state automaton to a probabilistic version, where you have a distribution over the choices of transitions and of emissions, then you're basically you now have this sort of probabilistic FSA, and with a couple of constraints and choices about how this works, you've effectively created an HMM. There's a deep connection between HMMs and finite state automata because HMMs are what you get when you put probabilities on them on the automata. And then building on what can finite state automata do for us. One of the really fascinating things that people were doing about 25 years ago in NLP was taking finite state machines and generalizing them so that they didn't just read a sequence or write a sequence, they actually did both. So they're transducing or transcribing from one sequence to another. So you can think of it as reading one tape and writing another tape. And these finite state transducers are just super interesting and super cool. You can also make them probabilistic, like with any of these symbolic machines. And there are a lot of ways you can do that, a lot of choices you can make about how to do it. And what this gives you is the ability to have composable stochastic relations between string to string, between strings. So you can chain together one string transformation on top of another string transformation.
And basically, you have all the building blocks to do inference and learning because this is all very similar to HMMs. The dynamic programming algorithms we used for inference and then plug into learning are incredibly similar to what you just saw in this lecture. And if you read the probabilistic FST papers, you would find it all very familiar, and there would be some trickiness in the implementation because some pieces are slightly different, but generally the whole thing has the same feel. And so some examples that I think are cool, there was a version of speech recognition where you would have this middle layer. You'd transduce your acoustic signal into phonemes, the sounds in a language, and then from the phonemes, you would have another separate modular transducer that canonicalized the words. So you could have two different research teams focusing on these two different mapping problems, and then plugging them together was a completely mechanized process. Another one that I thought was pretty cool about 20 years ago was translation between two near languages. So Czech and Slovak are different languages, but they share quite a lot of history. And there's a very I'm told a lot of the relationships between the morphemes are quite systematic. So the idea was to take the words in Czech, break them up into morphemes. Finite state transducers have been incredibly useful in morphological analysis and generation in NLP. Morphemes, by the way, if I didn't say it before, are chunks that bear meaning, often smaller than words, but not necessarily. In English, they tend to be about the same thing as words. In a language like Czech, they tend to be more abstract because Czech has a very rich morphological system that adds a lot of stuff to the words to inflect them and make them agree with each other, and add things like gender and number and so on. So that's your first transducer. Your second transducer goes from Czech morphemes to Slovak morphemes. That's your translation module. And then finally, you have another morphological module for Slovak, which transforms the morphemes in Slovak to the surface words. And so again, 3 different researchers could work on these 3 different parts, and then you could compose them all back together. This idea that you can decompose your NLP problem into these different pieces and study them separately was incredibly popular at one time, and now it is, I would say, fairly unpopular. There's a tendency to try to think about learning as an end-to-end process where everything influences everything else, and you plug in inputs and outputs, and all the stuff in the middle just happens to optimize your performance on the task. But the 2 views are actually not incommensurate at all. One really fascinating idea would be, I think, to build each of the modules by designing the architecture that's appropriate for that module, and then put them all together and do the end-to-end learning the way we like to do end-to-end learning, by following gradients. But still, the internal pieces would have been constructed according to what we know about each of the individual problems. And I think that viewpoint is starting to gain ground in NLP, and you'll see more thought paid to how we design architectures for different parts of the problem, and maybe have supervision or at least evaluation at different steps along the way through the computation path. Okay. We're about out of time, but I want to point in some directions that you might find interesting and are now, I think, well prepared to dive into. So this is kind of a laundry list of some additional topics that you could go on and read more about. The first is, when I introduced HMMs, I talked about these multinomial distributions. Multinomials over things like words and states are one way to talk about the probability of a thing happening, but featureizing or representing things like words or things like states as vectors has become incredibly popular and has worked incredibly well for many things in NLP. And so there's a connection between HMMs and these more feature-based representations, and learning those representations through various techniques from spectral methods or neural networks are an exciting pathway. If you want to do sequence modeling, representation learning is probably going to help you do a lot better. And the key here is that rather than thinking of the different states or words as completely distinct elements in a vocabulary where each one is just different from the others,
we can imagine them as living in an embedded space so that two words can be closer or farther apart from each other. And there are technical ways of extracting these kinds of representations, often from unlabeled data, that have been quite useful in NLP. We focused very heavily in this lecture on the generative HMM, but there are ways to transform them into discriminative models. The classic ones are called conditional random fields and max margin Markov networks. These are relatively straightforward extensions, and they reuse a lot of the computational machinery when you want to work with them and train with them. Hidden Markov models, as we said, make a pretty strong independent assumption that every state is independent of all the other states, given its two neighbors, and the words only depend on each other through the states. There are some interesting ways to weaken the independence assumptions. So, for example, there's something called a semi-HMM, where you go into a state and you decide how long to stay there before moving on. These are a really interesting solution to problems where you want to segment your data. There's quite a lot written about semi-HMMs. I wrote a paper a few years ago with my students that neuralized semi-HMMs, and that had some nice benefits. The estimation methods that I gave you I'll follow from sort of classic frequency-based maximum likelihood estimation, but there are alternatives. And one really interesting pathway are called spectral methods that are related to method of moments estimation. If you're interested in alternatives, and these lead to really some very cool algorithms where you don't have to do iterative hill climbing like the EM algorithm to estimate your model, then that's a great direction to follow up on. If you are a linguist or you are fascinated by the structure of language, then you know that finite state models are maybe not the most elegant way to capture the kinds of statistical dependencies we see among words in sentences and longer documents. And so there's a whole family of really cool formal models based, starting out from formal language theory, moving from finite state models to grammars. And so probabilistic and weighted context-free grammars are really, really fascinating next step on the path to modeling long-distance interactions and reordering and things like that. And there's an incredibly large literature on formalisms and including weighted and probabilistic formalisms for capturing hierarchical structure and recursion and so on in long sequences. And then finally, I give you a little taste of the idea of putting a prior on your HMM's parameters. That's a step in the direction of an area called Bayesian machine learning, where you have new inference and learning algorithms. One of the most fascinating things that people have done in that area is to take away the assumption that you start out knowing how many states you need for your HMM. So they call this model the infinite HMM, and the idea is that you don't specify the number of states; it emerges naturally from the data. So you have to have a prior over the number of states, and there are some really elegant tools for building priors over HMMs that are richer than just the parameters. And finally, I know you're wondering, why did he say almost nothing about neural networks? They're at the heart of everything we do in NLP now. And so I want to say just a tiny bit about neural networks before I close. You're going to hear more about neural nets, I think, in the next few lectures. But intuitively, it is true. Neural networks for sequences can do all kinds of things, meaning they can represent all kinds of functions over our sequences that finite state methods cannot. Finite state methods, like HMMs, and also like the Markov models at the beginning of our lecture, are inherently restricted in what they can represent. And we see that now. We often tend to see that as a negative. There was a time when that was seen as a very attractive property, because what we wanted, when the goal of NLP was more about computational linguistics than building practical systems, we really wanted models that could capture all the phenomena that we observed in language and none of the ones we didn't. And for some parts of language, particularly morphology, finite state methods do a really good job of capturing a lot of what we want. Maybe not everything, but because they do so well at the things they can do, they can be learned with less data, and they can be made much more easily.
But anyway, it's true. Neural nets can do all kinds of things that finite state models can't, and many of those are things we want to do today. They involve higher order processing and getting away from just the surface. So I'm not going to talk at great length here about what neural nets can do that HMMs and finite state methods can't. But I do want to put in your mind the idea that these differences are something that maybe can be studied in a formal way, not just using examples or kind of hand-wavy arguments. And so with some of my collaborators, I've been delving into this in the past few years. And so one interesting thing we were able to establish is the existence of a family of neural networks that are exactly weighted finite state machines. We call them rational recurrences. You can read our paper from a couple of years ago about this if it interests you. And the fascinating thing about rational recurrences wasn't that they were just a theoretical construct. It was that once we defined them, we were able to go into the literature and find 6 or 7 cases of rational recurrences where people had invented a new a new recurrent neural network, a new RNN, as an alternative to the dominant methods. That usually they were driven by computational concerns, sometimes a kind of interpretability, and we could show pretty easily that they were rational. And so, what is this bias? We have some more recent work published at ACL just a few weeks ago on building up a hierarchy of capabilities for recurrent neural networks, and with some beginnings of connections to the more recent family of transformers as well. So I could talk all day about this, but I'll stop here and say I think that knowing what kinds of restrictions might exist on models can help you start to draw lines around what the capabilities are of different kinds of methods, and so your sort of first order assumption might be we want the most powerful models we can possibly get. A more mature view recognizes that with greater capacity comes usually greater expense, both from a computational standpoint and from a data standpoint. To estimate a really powerful model that can do almost anything, you're probably going to need a lot of data to show it exactly what you want it to do. But a more restricted model can often pick up the concept much faster with less data and less computation, which is something that I think we should all be considering, given the potential impact of running massive experiments on everybody's budgets and also the climate. Okay, I will stop there. In this lecture, we covered some core concepts from NLP, markup models, mostly applied to language modeling, hidden markup models, mostly applied to sequence modeling, sequence labeling, the Viterbi algorithm for picking the best sequence, a whole slew of other inference algorithms related to Viterbi, and then we applied those within learning algorithms for both the supervised and unsupervised case of hidden markup models. I hope you enjoyed the lecture, and I'll be happy to take your questions.
Okay, I know we ran over time, and I'm sorry about that. This is kind of a new thing, doing the pre-recorded lecture, and I know the lengths of the lectures weren't quite what I was hoping. I wanted to do 6 chunks of 30 minutes. That didn't quite happen. Anyway. People have been asking questions throughout. I'm happy to take more now. If there is anything on people's minds, I know it's in Europe, it's getting late. This is the Lisbon Summer School I remember. Let's see if anything happened in chat. I haven't been watching. Somebody says they like the end-to-end approach. Yeah, I would. One kind of small note of caution here. The end-to-end approach is very exciting, but one of the big, and this is kind of getting back to one of the high-level things I said at the very beginning of the lecture. One of the things to remember is that the end-to-end approach makes sense when you think in tasks. When you think about natural language processing as essentially being defined around input-output tasks. But if you think about the full range of human language capabilities that we all share, it's hard to talk about them in terms of tasks. This is a very artificial construct that's very useful for making progress on in applying machine learning to NLP, but it is not particularly helpful to describe what humans can do when they use language. We can do a lot of different things, and delineating them into tasks, I think, is it's an approximation. It's not a great way to think about the full problem. And so that's actually, you know, I don't think anybody should be a partisan or religiously affiliate with particular techniques that we use in machine learning. I think that's a very unhealthy and dangerous way to think about these things. But it's better to think about pros and cons and advantages and disadvantages. And so this lecture completely embraced a generative view, not because I believe everybody ought to always do that. If you look at my papers, you'll see I certainly haven't done that in general, but the advantage, one of the big advantages of the generative view is that you can build a model that does a lot of different things. And basically any inference question you can ask about some variables given other variables, or coloring the graph in terms of blue and red and gray in the ways I used in the lecture, you can use the same model for all these different things. And that's, for me, quite compelling that you could build one model of lots of data from lots of different sources of evidence and solve many problems all at once. I know multitask learning has become very popular, but that's still fundamentally framing the problem as a bunch of input-output mappings. So I think that this complementary perspective is worth considering. One of the things that we used to talk a lot about in NLP and don't talk about much anymore, that I think was a very valuable idea, was the notion of modularizing capabilities. So you could have some people working on the morphology of the language, some people working on the syntax, some people working on the semantics. And if each of these components was independently strong, then you could put them together and make a larger system. And there were many ways of slicing and dicing the space. But that modularization allowed us to work in parallel on different problems and then piece things back together. I know this sounds very foreign to people who have been trained primarily using the end-to-end view. But I think it's, you know, again, you shouldn't be religious about these things, and the trends in the field will shift over time. What's popular today will not stick around forever as the most dominant thing. Okay, we have a question from Yvonne. How does the HMM relate to latent Dirichlet allocation? Okay, so this is an interesting question. There are some connections. They're both generative models of data. I'm not going to give you a full definition of LDA, but I'll point to a few differences. One is that LDA it's not a sequence model. It doesn't care about the order that you see the words. Another difference is that LDA is inherently Bayesian, that Dirichlet is referring to the prior over the parameters in the model. And you can have a Dirichlet on an HMM or on the transition and emission probabilities in an HMM, but you don't have to. And the default assumption, unless you say that you do, is that you don't. So that's those are two kind of important differences. In use, HMMs have been traditionally applied to things like words and sentences. LDA is more of a document level model in most instantiations. As far as I know, there isn't really, most of the time LDA is applied in a kind of unsupervised way, like to discover themes across a large text collection. The latent variables tend to be interpreted as topics rather than as something like part of speech tags or syntactic states. But if you draw the graphs and you squint your eyes, you can see a lot of similarities between these two things, and you can find models in the literature that bring the two elements together. There are versions of LDA that are sequential. There are versions of the HMM that use Dirichlet priors. All of these things have been explored, and I think you can't really fully understand the full set of them unless you get the grounding in the kind of graphical models way of thinking and Bayesian parameter estimation. That's a great question. More in chat.
Okay.
The person who likes end-to-end also agrees with modularization. Yeah, I think figuring out how to both modularize and get the benefits of large-scale end-to-end training is an interesting direction.
Okay, I guess that's it.
Time to stop.
Thank you very much, Noah. for the great
Thanks,
talk.
everyone. It was an enjoyable day. I hope you you learned something, and please enjoy the lectures from my friends over the coming days. Have a good evening.
Okay. Bye bye.
Bye. Bye, Noah. Thanks for the lecture. Okay, guys. So.